Good morning, ma'am.
Morning.
Yeah, good morning, ma'am. Good morning, Jenny, ma'am.
Can you hear me?
Hello, ma'am. Are you there?
Can you, yeah, can you hear me?
Ah, yes, yes.
Thanks.
Ma'am, madam, do you want to try sharing the slides and see?
Sure.
Yeah.
Can you see my screen?
Oh, yes, yes, it's okay. It's perfect.
Yes, ma'am.
Okay.
Ma'am, we'll be starting in a short while. Participants are joining in.
Sure.
Good morning, all. It gives me great pleasure to extend to you a very warm welcome on behalf of Department of Electronics of toch Institute of Science and Technology to the first session of Day 5 of Phase 2 of AICTE-sponsored 6 days short-term training program on the topic Robotics, Artificial Intelligence and Control. Today's session on the topic Robotics in Data Warehouse Management is handled by Ms. Janani Mohan. Ms. Janani graduated with a bachelor's degree in Applied Electronics and Instrumentation from College of Engineering, Trivandrum. She worked as an embedded software engineer at Bosch, Bangalore, before moving to the US for master's. She has a master's degree in robotics engineering specializing in swarm robotics from Worcester Polytechnic Institute. At Venka Robotics, Ms. Janani works on developing algorithms for multi-robot coordination. She tackles real-time resource challenges at various client sites, working towards designing optimized robotic software. The world of machines and automation has always inspired her, and she enjoys making fun hobby projects. Apart from robotics, she is passionate about learning new skills and spends her free time with her plants. Now, I hand over the session to Ms. Janani.
Hello, everyone. Thanks for giving me this opportunity to share some of my experience while working in a robotics industry. So today I'm going to have a short presentation specifically on the topic robotics in warehouse management. I hope everybody can see my screen. So,
Yes, ma'am.
Good. Okay, so today, so just like an overview, what we're going to discuss is basically a little bit of familiarization about who am I, and then a little bit on my experiences of coming to the US and doing masters in robotics engineering. Then we'll discuss a little bit about industrial robots as such, and then go into understanding what warehouse management is in a real world scenario, what's its relevance, and how a real world robot development plays an important role in that, the different kinds of robots which are deployed in warehouses currently to support various activities within the warehouse, and some of the challenges which are like commonly faced when we actually have real world applications compared to like research, which is quite different from how we actually have applications on a real world warehouse system. And towards the end, I will just like brief about what we do at my company called Vecna Robotics, and also explain a lot of some of the future trends which we see in this particular industry. So about me, I think as already mentioned, I had graduated with a degree in Applied Electronics and Instrumentation from College of Engineering, Trivandrum, and then I worked for 3 years at Bosch, Bangalore, mostly on the embedded side with ECU design and intervehicular communication, and I moved on to do a master's in robotics and automation at Worcester Polytechnic Institute. It's in Massachusetts, and now I'm working as a robotic software engineer at Vecna Robotics. So some of the common robots around us, this is just like a very basic introduction slide, and I think most of you would be familiarized with almost all of these, but just to give a brief idea on some of the challenges which we face in each of this and how an industry looks like for each of these robots. So going to domestic robots, I think one of the most common applications right now is like vacuum cleaner robots, and this particular one is called Roomba by iRobot. So it's pretty common in the US, and it's mostly there in everybody's house. So one of the most common challenges by using indoor robots is like it has to first understand how your household looks. So it's kind of like mapping the environment, trying to gauge where the obstacles are located. And since most of the items are like static and doesn't keep moving within the house, we can say it's most close to a static indoor environment rather than a dynamically changing indoor environment. So these robots have like basically a couple of sensors which are towards the front of the robot, one's for obstacle detection and some for basically trying to understand the distance to the walls, like sonar or something like that, which can help it to gauge and move around inside the household. And with that, I think they have also provided some suction techniques for like actually doing the vacuum cleaning functionality itself. Next comes the industrial robots. So this is what is mainly we're going to discuss in this small talk. So industrial robots are I think we are very familiar with robots, which are like mostly fixed robots, which are like placed at a station, and then it has a manipulator, a robotic arm, which moves around and which has some degrees of freedom, which helps to move objects from one place to another. But with more revolutionization happening in the industrial robotics field, now there are vehicles such as AMRs and AGVs, which are like more popular in the industrial field than just fixed mobile robots. The next part is medical robots. So this is another field which is very upcoming. And when I was doing my master's, so we had a lab which was dedicated specifically for medical robots, and the specialization was like in surgery. So those robots have to be very, very skilled in the sense of the accuracy for those robots, and those manipulators should be very high. So the algorithms which are used for that is specifically designed so that it focus on precision rather than on like time or the speed at which the activity is done. It's more on the precision side of things. The fourth type is basically commercial robots. So this is a pretty famous. So we have a company called Boston Dynamics, which specializes in these kind of robots. So this is specifically a robot which is trained to have behave like a dog. The idea of these robots is basically in military applications is what they are envisioning these robots to be used for. So they can be used for carrying medicine kits, or it can even be some kind of logo like explosives. That's like the extreme form, but mostly medicine kits in military applications. So that goes and like delivers that to the soldiers when they're out in the field. So these kind of commercial robots, so those companies, they're not specified like sell it to the like customers like normal people. It's basically for very commercial applications which can be used by the DARPA, which is like a defense stream in the US. So those are some of those robots. The next is automotive applications. That is, it goes like way back. So I think the start of robotic industrialization started in the automotive field, where for manufacturing cars specifically, we have this very huge fixed robots that are basically manipulators, and they help in welding and different other applications of placing different parts of the cars, as well as like designing and aligning the whole car itself. So that is it's one of the oldest applications of robots. And the last three parts here is like the most recent applications, or something which is like thriving and the latest in the robotics field. So first is like self-driving automation. That is like you all would have heard of like self-driving cars. So the whole technology relies on something which is completely autonomous and which requires like very little assistance from a manual driver. So ranging from Tesla to Google to different other companies, including Uber, they have launched a lot of self-driving cars. They're currently running here, even in Boston. So we can find out, like if we go on the streets, we can see self-driving taxis and all of them running around. And the basic principle there is a combination of sensors as well as different navigation mechanisms, and using already well-developed Google Maps, which has mapped most part of the world and like developed a clear map, and using real-time data in synchronous with those maps in order to like actually guide the vehicle to go from one place to the other. The next part is exploratory robots. This is like very interesting field, and many people are like interested in, like usually like the younger generation right now, they are inspired to like develop robots which are for exploring outer space. So this example is that of Curiosity, which is currently deployed by NASA in Mars. And I think even ISRO in India is like they have their own robot capsule, which is going to be deployed soon in their next mission. So this is like a very upcoming field, and people are like super excited about it. And the last part is the humanoid robots. So this particular robot is called Valkyrie, and this is also this is developed by NASA specifically for their Mars mission. So sharing my experience with that robot. So when I was doing my master's, I had participated in a DARPA challenge, which is with the Space Research Challenge, which is a part of NASA. And the whole idea of that challenge is to actually program this humanoid robot to actually make it do different activities. So the most challenging part of a humanoid robot, as you can see, is that it has like different so you can consider that each part of it, like the arms and the legs, are like have different degrees of freedom, and each of them have a lot of control mechanisms associated with it. So for making it move from one place to the other, there's like heavy reliance on dynamics and control, and vision definitely plays an important role for us to guide that robot to move from one place to another. So it was like very super challenging, and maybe towards the end I can talk a little bit about it. So these are like some of the common fields which I've come across, like with when I was studying, as well as with the different industries I have interacted with. So moving on, today's topic, we're going to focus basically on industrial robots. And I think the first part of it, or like pre 2018, 2017, we were mainly still heavily relying on like fixed industrial robots, which are basically manipulators. That's like it just has an arm which keeps moving, and that arm has like different degrees of freedom. It can be 3 to 6 degrees of freedom, and it is used for a varied set of applications, including pick and place and including pick and place. And the latest trending technology right now in the field of industrial robot is what we call the AMRs, which is the autonomous mobile robots. So, and they actually have play an important role in the they play an important role in warehouse management, and this talk will mostly cover a lot of important points about the autonomous mobile robots rather than the manipulators. So this is an example of, like, again, this is a project which was done by me, and I just wanted to give an example of like an industrial robot which can be like tuned to do some specific purpose for even like for a simple research project in college. So this one, this project is basically for actually, so if you see there's a small PCB chip there, and the idea here is that I want the robot to like pick that PCB chip, find the location of it in the table, pick it up, and then place it on that PCB, and then finally it has to do soldering. So so this manipulator has like, I have connected a tool end, which is not like this video doesn't capture it, the suction part of it. So ideally it has an computer vision algorithm, the image processing algorithm, which kind of figures out where the location of the object is, and once it knows that, it goes to that particular position and then picks it with that suction tube, and then finally it finds out where should the end effector position should be, or the destination location should be, and then it goes to that particular final chip, detects it, and then places that particular chip on top of it. So this is just like how so for actually developing this on a real robot like this, there was a lot of challenges, starting from first interfacing with the hardware, as well as like making sure that when we have like a real world image capturing, as well as render, like using that image and mapping it to the world coordinates, is something which was very challenging, and the lighting conditions and a number of other factors played an important role in deciding how well the robot performed. It also it also like the choosing of the sensor as well as the end effector or the actuators are also like equally important while designing like a hardware product in itself. So this is just like an example for the industrial robot, and I think most of us are like familiar with this robot, and I think most of the time we have been like learning more about these robots in our curriculum. But right now the most trending thing is autonomous mobile robots. The functioning of these robots would appear to be like very simple in general, because it would be just like robots moving around and doing some pick and place activities. So for example, in this video, this robot, so this is an example of like a typical warehouse scenario, where you can see a set of racks and we have aisles in between. And these racks are mostly positioned at specific distances, and they have a lot of things stacked one on top of the other. So the idea of these robots are basically they have to go through these aisles, and then they have to like go to that particular rack based on a number, or it can be a position which we would have mapped in advance, and then it has to go to that shelf and then basically place that particular tote. It's called like a tote retrieval system or a retrieval mechanism. And there are ways like, so this is an example where there is both a human robot interaction, as well as actually the human itself goes and then interacts with that particular package, takes it, reads it, and then places it back in the tote, so that later the robot can itself go and retrieve it. So the main role of humans is basically to like choose the right packages, because they are more knowledgeable and they are more aware of it, but the actual shipping or moving of these packages from one place to the other, basically the lifting, carrying, and transporting parts are done by the robots, because it's more like a mechanical work, and then it doesn't require a lot of efficiency from a human. So this can be easily done by robots and can be automated. And yeah, definitely. And one of the most important aspects of any real world robotics application is safety. So it has to be good enough to avoid persons as well as other obstacles in its path. So yeah, so this is an example of this is like a base example which I wanted to show about autonomous mobile robots before we jump into like understanding more into how they are used and what are challenges which we see. Yeah, so this robot is kind of very sophisticated. They'll actually show you how they have designed the entire arms and how it. So as you know, robotics is like a field which integrates many different fields of engineering. Not only like you can't say robotics is just one field. So it's a multidisciplinary field which has mechanical design, electrical, as well as a lot of software for detecting and processing information. Yeah, so I think this company mostly specializes in, so they advertise saying that they are good at working with any different kind of environment, specifically for picking different packages and moving through like different arenas, so that they can help in moving items inside the warehouse as well as like outdoors too. So this is an example of it being used outdoors. Okay, moving on. Okay, now we come to our main topic as warehouse management. So warehouse automation is kind of like one of the biggest trend right now in the industry. And we all know mostly why, because the way people like shop as well as like send items have like revolutionized over 10 years back. The way we used to go to a shop and buy things is way different than now. We order everything online and things come to us. Either people deliver or so basically it's like a whole warehouse of all this goods stacked in different places, and somebody has to go and pick them each time and then find out which address it has to go through and then go and give it to somebody and they go and then ship it. So now that we have revolutionized the way we shop and then the way goods are even like advertised and marketed, warehouse management is like a key player in an application for robotics. So as you know, some of the basic things why we need to use a robot would be that a lot of activities within the warehouse is like routine and is repetitive. So all those applications, we want to make sure that we can automate it to something which is beyond a human capacity. I mean, human can be, so certain aspects in which robots are better, certain aspects in which humans are better. So if we can give the right roles and divide that, it'll make both the lives easier. So that's one of the things which we are always trying. So whenever we try to go and deploy a robot in a warehouse, the first question they ask is, will humans lose their jobs because robots are coming into the market? But that is, that's the answer for that question is definitely no, because the strengths of humans and the strength of robots are totally different, and they both complement each other rather than being like opposing each other. So so specifically for improving efficiency, productivity, as well as like replacing all the work which require a lot of effort from human, like strength wise, as well as any repetitive jobs, that's where the robots play an important role. So these are some of the things which in general like reduce shipment, time to shipment, waste reduction, efficiency with safety. So all those are like some of the important aspects which are required in a warehouse management system. And recently, with this year being very different from other years and we experiencing COVID and all, so during this time, like with my experience is that currently, since humans are not allowed to interact a lot with each other, and the number of humans who can work in a warehouse environment has to be like reduced to a minimal level for safety purpose, robots are becoming like, they are the best persons right now, because they can be a substitute for humans and they can actually do the job for us, because people are still shopping, people are still getting things. So if humans are not there to go and do it, who can do it? So that's when these robots are actually playing a big major role right now. So next thing I want to talk about is something called Industry 4.0, and this is kind of a revolution that's happening right now. And the most interesting part of it is that it not only like focuses on automation in the form of mobile robots or robotics itself, it handles so many other parts of some of the terms which we normally hear, like big data analytics and then cybersecurity, and like how do we store data, how do we store information, like if you're running a software, where do you run it? Do you run it inside a machine? Like before we used to have like just computers where we store everything inside the computer and run it inside that. Now we have moved into a space like having everything in the cloud and spinning up virtual machines and running software in that, so that it's detached and it has a lot of space and it's like reconfigurable. So there's so many different advantages. So we are like moving into the field of exploring different ways of handling information as well as data, which is much more safe as well as easy to integrate with new systems. So most of this are like the trending things, and yeah, the focus is again on like smart devices and smart factories. So the idea is that a complete connection between customers to like different locations to where the inventories are, and how the demand is based on the demand, how to do the distribution, and which products have to be delivered first, or yeah. So there are like a lot of logistics involved in it, and the supply chain management plays an important role. So integrating a supply chain management pipeline to a robotic system, or even like the entire workflow to involve robots in it, is something which is happening over time, and it's kind of like the current trending thing in industry 4.0. Cool. So the next part here, we're going to just talk about some major elements in warehouse management. So as you can like imagine, so basically a warehouse scenario like this image says is like, it has like somebody packages the items, then takes a barcode, prints it, and then attaches to that particular good, and then it can be like, first we get the stock, and then once we receive the stock, it's classified, and then we document it, and then after we document, we allocate it to different locations in the stack or the racks, so that as and when time comes, they are picked up from the stack and then packaged and then dispatched. So this is the entire cycle of it, and you can see that most of this are done currently by manual, like by humans. So they use like vehicles which have forklifts, or it can be trucks which can be driven by humans and which pulls a set of different like heavy pallets or heavy articles in it. So all this are currently done by humans, and they actually do this manual work. So the idea here is that what part of this can be actually automated to be done by an external entity. For example, it can be a robot. So how do we do that? So so for each and every step of this, there is some part of it which can be automated. So it need not be just by providing a solution as a mobile robot, but it can be also like a technology. And that technology can be a software. It can be a new technique, like maybe using something like machine learning to understand how the whole dynamics works, and then deliver it in the form of information which can be tracked over time and then predicted. Like, so consider that this many stock of items came, and over these months, it's going to be like reduced to this level. So can we actually predict the demand workflow? What happens at that point of time? With that, can we like say that, okay, during this period of the year, it's like the peak time, and then these many robots needs to be deployed at that time, and this many humans need to work with that robot. So coming up with all these numbers in a real world scenario is like one of the challenges which any company who's working in this field faces. So we have to come up with, understand what are the challenges they are facing, and how to like bring an optimal solution to their problem of in a particular warehouse. Okay. So these are some of the common use cases for the autonomous mobile robots in a warehouse management. And okay, quickly going through them. So first one is like loading and unloading. So these are specifically for warehouses which deal with like really so those packages which need to be loaded to a particular truck. It can be like moving into a truck and placing it, or it can even be like in a rack. So all of those are basically loading and unloading applications. Palletizing and depalletizing is like, so in some places, all the goods are packed in something called a pallet. So it's like a rectangular box, and top of it, we'll have a big like a container, and inside that the goods will be there packaged with sellotape, or it can be even tied with strings. So all those are so that we call a pallet, and each robot has to go and detect a pallet, go under it, and actually pick it up and place it somewhere else. So this again, it's kind of picking and placing also, but the technical term they have used is like palletizing and depalletizing. And so the example of that pallet would be the bottommost one, if you can see the mouse pointer. So that is what is called a pallet, the light brown one, which that forklift is trying to lift with the white goods on top of it. So that is the pallet. So a common application is like picking pallets of those sort and moving from one location to the other, because otherwise, again, these are done by fork trucks, which are run by manual drivers. But now we are trying to automate them and make sure that these robots can automatically go and pick up these particular goods from one location and place it somewhere else. Sorting, picking, and packaging and transportation, they all form like a cycle. So it's like sometimes so sorting is a very good application where we can use a mobile robot with an arm. So for example, if there's a truck, there's a can of plastic bottles and maybe some other elements like a small ball, so we can make this particular robot detect the balls alone or the plastic bottles alone and then just sort them together into two different bin. It's called like bin picking or bin sorting. So that's kind of an algorithm which is used in like industries. For example, in a food industry where they want to actually segregate different food items stored in different containers and group the containers together. One common application is basically using an image processing algorithm or computer vision algorithm and then try to sort out goods in a particular bin into different bins with labels on it. So it has to like not only while selecting the good, it has to use algorithms and detect them, but also like finally to place it in a particular destination, it has to do a set of algorithms and then go and place it in those containers. So sorting, picking, packaging, and transportation kind of falls in the same thing. So delivery is another application. Even within this space, one of the robots which is not listed here is the aerial robots. So that's like it's a trending field, but the problem with aerial robots is that they are not very fail-proof, or the safety aspect of it is still not proven. So if you're using it, even if it's an outdoor environment, most countries don't have like good licenses for drones. And even I think it's mostly allowed close to industry, like colleges or universities only support testing drones in the United States, but in some other places, I think they do have commercial drones which can be done. So drones also are like a field where people are trying to see whether how useful they are in like delivering goods. And I think you would have seen the advertisement of Amazon drones which are going and delivering some goods. It's actually like a way of advertising it, but it's not like a well developed and fully implemented field. So replenishment is more like if there are like shortage of goods. So this is the part where it comes where not only we are selling the product as just something which can move items from one place to the other, but also some kind of a software or technology which helps the customer or the warehouse itself analyze what it has in stock and what is needed. So in case of replenishment, how can we replenish the data? So like data is in the form of like goods or services. So it can be like a predictive algorithm which kinds of predicts at what rate things are going to get replenished and how we can like actually meet those demands when it comes up. So now we're going to some more like technical aspects of like understanding if me as a company want to like deliver autonomous mobile robots for a warehouse management application, what are the things which I need to look forward to, or what are the real world challenges out there? So starting with the physical specification for AMR deployments. So this is an example of like a forklift truck. And this is an example, it's just a picture of a real warehouse present here. So first thing before we start a deployment at a new site would be to understand how the warehouse itself looks. So some important aspects over there would be like how much area do I have to cover? And the other would be like the number of racks and aisles in that particular warehouse. It can also be a good way to know the height of the racks, and then comes the part of, so once we have this basic idea of how the area looks like, what are the different heights the robot has to reach, that's when we kind of decide how to like develop that robot for it. Or mostly all companies which work in the field of warehouse robotics have at least more than 2 to 3 products, and they are used for like different applications. One would be for like pulling heavy goods, other would be for lifting or like picking up and placing somewhere, and some of the others are like low lift trucks, high lift trucks. So based on what the warehouse, how the warehouse looks like, the robots are being designed or deployed at that particular warehouse. And the important things there is that so one of the first major things which we have to do is like to understand the environment is basically to map the environment. So mapping is like kind of deploying like a mapping algorithm. So we basically run the robot entire warehouse and do kind of localization. So there's like localization and mapping is like a common technique used for any indoor navigation system. So first thing we do is basically run it around that warehouse and do the mapping, understand like how the robot perceives its environment and create a map of the environment. So it's only after that basic idea is done, it generates this map of like static obstacles, and that's going to help the robot to do what we call the navigation, like basically obstacle avoidance and detection, etc. So the first part is basically the physical specifications, which depend on how the warehouse looks, and based on that information, we kind of derive how my robot should look. So the dimension of the robot and the lift height, all that depend on the size of the rack, the aisles, as well as what height the folks should go in order to do pick and place activity and things like that. Same goes for the fork length. So if they have to pick a pallet, the pallet is bigger than a small box, so it has to have a bigger forked truck rather than a small forked truck, and things like that. Yeah, the second one is a functional specification. So here, so this part is basically understanding what is the amount of demand we have to meet with the robot, and this helps us to like understand, okay, how many robots should we be deploying in order to meet that demand. So the first thing from the warehouse side, which we would be expecting, is things like how many orders has to be picked up and delivered to the racks, and what is like the order workflow, like yeah. So different warehouse industries have different workflows. Some people will be like how we saw like removing from the truck. Some of them will already have some other mechanism like conveyor belts, which will be taking goods from the truck and then depositing it in one place, and the robot has to go and pick it from there, keep it in the rack, or place it somewhere else. So it's like understanding the order workflow is like plays an important role in designing how the mission workflow or a task workflow for a particular robot actually works. So that's yeah, that's the second point, the order workflow, and then the influx and efflux rate. So this is the rate at which so that's something which keeps changing. So as you can see, sometimes it's like Christmas, so everybody wants to buy gifts. So at that point, the purchase rate would be high, and the amount of goods ordered would be more, and the amount of goods leaving the warehouse would be more. So at that time, it's like the peak time for the particular warehouse, and at that time, the efficiency rate or the productivity rate is something which they are like very focused on, and they want a lot of robots at that point to like work in parallel or like in synchronous modes, that they can get the job done like much faster. So yeah, so understanding that is like very important. And finally is like the error rate and performance metric. So as you know, any system will have a little bit of error rate or failure rate due to any of the circumstances. Like it can be that it gets stuck somewhere, or it doesn't know, it loses Wi-Fi, or so how do we gauge that, and how well the connectivity is there. So we kind of do a connectivity test inside a warehouse before we go and like actually deploy the robot. So these are some of the things which we need to keep in mind. And yeah, so once we get all the specification from the warehouse, the main idea of like the development team or the core team, which is like working on designing this algorithm, is basically to understand, okay, how many robots now should we be deploying, and what are the different features we need for the robot. And one of the most interesting features, or something which is like everybody enjoys, is like when a robot is running around in a warehouse, people want to interact with it. So they want some kind of human robot interactions also, which makes it like a good way for us also to divide the work between the human and the robot. So some of the inputs which the robot requires can be given by humans, and then together they can work asynchronously to actually do the task better. So next is the safety specification, and that is like I would say the most important thing in any robot deployment in any place, because more than it actually doing the task, it's even more important that it doesn't cause any damage in the form of like hitting a person or hitting the rack itself or damaging the good itself or crushing something. So all of those things has to be taken care of. And currently we have two standards existing for that. One is like the European standard and the other one is an American standard. NANSI is the American one. But if you see that it clearly says something like driverless trucks and AGVs, and they are not actually mobile robots. So since mobile robots is kind of like the latest technology, we still don't have like a well-defined standard for it. It's mostly whatever was applied to like driverless trucks or the automated guided vehicles, the same standards are being applied to the same as AMRs. But the key core idea is that that should not be a single accident in a warehouse. So that means more than giving preference to like the speed of the robot, more preference is given to something like obstacle detection and collision avoidance. So that is why we have like lot of things here like emergency stop system, and then personal overspeed detection. So it's like somebody comes in, they have to understand who that person is, so as you know, like if something moves at a very high speed due to the inertia of motion, the time for it to actually stop would be much larger, or the distance for stopping distance would be more. So that's why we say like a safety limited speed. So depending on the traffic rate in that particular warehouse, it's very important for us to understand what the safety limited speed should be. So these are kind of some of the complications when we start designing a robot for a real world scenario, because more than like making the robot do a particular task, it's much more important to make sure that it satisfies set of safety conditions and make sure that it doesn't cause any damage, because that's just one set of that can have a very bad impact on actually like deploying more robots in a particular place. Yeah, the next part is what we call the workflow specification. So workflow here is like, so as I said that every warehouse will have some kind of a new workflow in mind. So one of the examples is that like previously, if you see that in industries, we have conveyor belts, and conveyor belts are basically used for moving goods from one place to the other. So even if it's in the food industries or textile or any of them, the initial automation in that industry was like conveyor belts. So most of the industries, what they're doing is that they don't directly go into the automobiles, the autonomous mobile robots. Instead, they do the migration part. That means they have conveyor belts and we might have to interact with another existing technology. So the workflow or the use case here is like whether there are existing technologies. So that makes it more challenging, because it means that we have to work with an existing workflow, introduce our system, and then make sure that they all work together in synchronous. So the important part there, as I said, is that to understand what the existing workflow is and then inculcate the role of the AMR, or understand how my product can play a part in that particular scenario in order to make their efficiency better. Yeah, and in that that the important part again is the human robot collaborative workflow, because we have always emphasized the fact that humans are definitely more smarter than robots. Although we say smart machines and smart vehicles, they are smart in the sense that certain things robots can do better and certain things humans can do better. But together is when we actually bring the best efficiency out in any scenario. So the approaches which most of the industrial companies follow is like a human robot collaborative approach. Yeah, and the last part I think is the operational specification. And here the idea is again to decide how the software and the hardware should work for the use case. So here what I mean is more in the sense of now that we have defined the use case and we have defined the scenario, and they would have given us like all the aisle specification and everything. Now is the real part of like designing a machine, and we have to understand, okay, so what are the sensors I would require? What exactly would be my encoder, and what kind of mechanisms like plug and play? Should I put a forklift or should I make it a tugger? What should be the use case? And the next part of it is like designing the software. And if you think of like how the software works, there are like different ways in which we can design software, like in a it can be a distributed system, it can be a centralized system, then it can also be things like do we have to go into the place where we want it for the robot to have just like a centralized server robot communication, or should it be a multi-robot communication between one robot to the other? So how do we decide all those factors? So that's where the challenges like keep mounting. And after we develop all the systems and like actually deploy a robot, the most important part is like training the warehouse workers to work with the robots, because more than us designing a robot which we can understand, it's much more important to design a robot which a person who's using it can understand. So this is like what example that shows there is like it has a UI, which is like a screen, which mostly will be a tablet, and it will give some information for any user to interact with the robot, as well as have information from the robot on what it's doing, so that they can work synchronously and understand their workflows better. Okay. Now we'll go into a little bit into more technical aspects of things. So what are different components of an AMR in a workhouse application? So if you see here, as I said, so first thing when we go to a warehouse is like, first part of it is like mapping. So we go and understand how the whole arena looks. We do the mapping of the arena, understand, okay, so this is how it is, and then we generate the map of the world with static obstacles. The next part is like using our sensing system in order to sense out the dynamic obstacles. So that's where it's very important in understanding what are the different sensors required. Can we actually collaborate and use different sensors like sensor fusion to do sensing of obstacles, as well as racks, as well as, so when it comes to like picking from pallets, pallet detection is an important thing. Other robot detection is an important thing, because we don't want to run over other robots folks. So how to detect all these things forms under sensing. The navigation part of it is again like different algorithms can be used for moving from one place to the other, and I think most of you would be familiarized with like the Dijkstra algorithm, A-star algorithm. So all of this are like so they're kind of the most efficient and the simplest algorithm, and they can easily be implemented on all the systems. But the real world challenge there is always finding the right balance between the navigation side of it, as well as like the time and efficiency. So the measure of navigation is usually the planning time, as well as the time in which the deliverable is actually met. And this has to work with the sensing mechanism. So it also depends on, while we choose the sensors, what rate at which we are getting the frames, how well we can process the data from them, how well can we define the what we call like a cost map, which is mostly like a grid of black and white regions. Black is like occupied and white is not occupied. So how well can we build that grid map or the cost map of around us? So all this play an important role. And once we have this basic mechanism working, that is like the robot is able to move from robot basically knows where it is and where every single other destination is located. That's when we can actually go to the phase of like task execution. And what task execution means here is like, so we'll have a order from somebody saying, okay, I need an iPhone and it is in rack 53. So the robot has to go and first recognize, okay, rack 53 is in this particular location, which we would have defined in the map. So it has to move from plan A. So the task here is we'll say like it's called a pickup task. And it goes from wherever it's located, current location, source location, to destination location. Then does the pickup of that particular iPhone from rack 53. And then we will say the drop-off location is so-and-so. So it goes from there to the other. So this is like a task execution workflow. And when this task execution happens, so we can have like an orchestration engine which kinds of decides which robot is best for this task. So this is where the concept of like the multi-robot system comes, and how well we can develop algorithms which can help in the distribution of these tasks between a set of robots under different constraints. So the constraints can be the distance, it can be the time, it can be the effort, it can be the cost. So all of this come into picture in the task execution field, and that is something what we can call like a fleet synchronization or the fleet orchestration. So there's like a fleet of robots, and we want to like give it a set of tasks which can be done either in parallel or asynchronously. So So all of this task execution is a very common term in computer science also, which most of our computers are doing, like parallel processing and everything. So something similar can be even applied to a real world resource like a robot. So that is something which we have to design based on the application. And the and doing, apart from doing all of this, it has to make sure that it is working in a safety constrained way. So at each step of it, it has to make sure that we follow the safety constraints and like avoid obstacles at all costs. So moving on, the last, yeah, and coming to the close. So challenges of the AMR. So this is I've divided it into like 3 sectors based on what we have discussed: the sensing, navigation, and the task execution piece of it. So when we do like decide the sensing algorithms or the sensors itself, what are the things which are like play an important role? First thing, as I said, is like the sensor accuracy itself. So how well are we getting the frame rates, how accurate they are, how much pixel value they have. From that, how well we can process information. So all that play an important role in deciding what sensor has to be used. Second, and second point is like one of the most important points is deciding where to place your sensors. So some sensors are better equipped for obstacle avoidance, and we want it to be near the ground levels because that helps us to see the ground plane very well. Some other sensors which are used for like localization, they need to be at some more higher level so that we can see a larger area and cover robots behind us, in front of us, and side of us, like around us. So some of them are like 360-degree view is something which is very important. And for some other applications, we go for choosing cameras instead of like sensors, which are like LiDAR or other technologies. We actually go for cameras itself, which can help us give a complete 360-degree view around us. So some of the like trending technologies would be like Omni Eye camera, which is like it's, as the name says, it's like Omni. It can see all the directions. It's a 360-degree camera which stitches images from different planes and together projects it to us. So sensor positioning is like very important in any autonomous mobile robot because that decides how well we are able to understand our environment as we navigate through it. Sensor limitation is that, like, as any sensor, as they would be given the specs, there's always a limitation for certain for each of the sensors. Some of them are really good at doing like 3D point clouds. Some of them would be good in like just having 2D images, and some of them would just be like 1D. They're just going to like spit out a ray and we can do a ray tracing and get back what is happening. So understanding sensor limitations and like using them in basically gathering the data from each of them and using them properly is like, it's a very important application as far as an AMR is concerned. Yeah, and the other thing is that so environment plays an important role, as if you're like when we use sensors like in a real world application, the environment is the deciding factor for the sensor, because the light conditions will change, reflectivity of the environment will change, the floor would be different, uneven. So how does the sensor perform in all those conditions? And how, similarly, like there's a difference between an indoor environment and outdoor, because we're going to have lights from different type of bulbs at different points of the day, and then things are going to change. There might be wrapping. So how do we actually handle all of those is what is like the indoor environment specification. And the last one is sensor fusion. That's like the trending topic right now. That's like understanding how we can like gather data from different sensors placed at different parts of the system, and then use all those information to finally decide what the robot has to do. So fusing information from different sensors and actually creating a final output is one of the most interesting field, and it's like the trending field in the field of computer vision. And yeah, it also like, so this sensing mechanism is not only like in robots, even like self-driving cars use these kind of sensing mechanisms, and they play an important role. So if you see like some self-driving cars, they have a LiDAR on top of the car, and that's like the major one. It's going to give the entire view of the car, like towards the side, front, pedestrian, everything. So yeah, so sensor fusion is like is commonly used even in self-driving cars. The second part of it is navigation. So once that we know where we are and what is around us, the next part of the robot is to decide how it has to move to do something. So So the most challenging part of navigation is basically computing how well the navigation algorithm would work, or the computation time and computation power. So we can see that like how we decide to like spec our computer. We say, okay, 256, 1 terabyte memories, 12 GB RAM and all that. Similarly, any hardware or the mobile robot itself has a CPU or a specification which it can do, and the processing power of that is like very limited based on how much space and availability is there. So any algorithm, whether it's for sensing or for navigation, it has to be well under the computation power which can be supported by that system. Same goes for the mapping challenges. So the mapping challenges, as I said, that usually we use localization algorithms which are used for helping us like do a closed loop kind of mapping, so that we can start at one position and we come back. It actually completes the whole map and stitches the images and makes the final map for us. So all those can change based on how the environment looks and how well the algorithm itself works. And the next part of navigation is the dynamic environments. So when the map is created, the environment is mostly in like a position, and in an indoor warehouse environment, always things are changing. So how do we deal well with the dynamic obstacles, and how well the robot responds to it and updates its map according to it? That's very important. And that also has an impact on the computation power of the robot, because it should have good computation power in order to actually synthesize and process these obstacles quickly. Otherwise, the robot is going to be very, very slow when it moves along that path. Path recovery is that when it actually encounters an obstacle, how well is it able to recover around the obstacle? So there is again a lot of algorithms which are like involved in that, how well it's able to decide the distance between the obstacle, and how it decides whether should it actually go around it or just wait for it to move. So these things would be very easy like for us humans when we drive a car, because we are so used to it, and we have a better learning and gauging ability in our brain. But tuning the robot to actually do this at each point of time, like in a very dynamic environment, is pretty challenging, and that in turn affects the speed of the robot. So one of the important things in a real scenario where humans operate machines and robots are trying to be like competing with them is that everybody expects robot to move as fast as humans. And for us, we are much more like flexible in the fact that we know when to brake suddenly, or we will just like slide or turn around and do things when we actually manually drive. But when it comes to robots, and specifically when they're autonomous, it's pretty challenging to like meet the speed constraints as well as do the obstacle or the path recovery constraints like hand in hand. So those are like some of the challenges in the navigation field. And the task execution is like the next part of it, and something which is like so more than just deploying robots which can move from point A to point B, like point to point navigation, people are now expecting it to actually do like a workflow management, like define an execution workflow, like moving things from A to B in a round robin fashion. Like a robot goes from A to B, and the robot goes from B to A, and then it keeps on doing that round robin fashion of doing some kind of scheduling task or execution. So that's kind of where we are, as well as defining an execution workflow is. And again, similar to how the navigation time and computation time is, that the execution time is very important, and it's one of the biggest constraints when we are doing this kind of like pick and place task, drop off tasks, or even like moving heavy goods from one place to the other. The next part of task execution is like deciding how we want to do the multi-robot coordination piece of it. So some warehouses want multiple robots to collaborate together to accomplish a particular task, but in some other use cases, it is mostly like centralized and not distributed. So a centralized server will just give demands or tasks to different robots, and once they receive that task, they all work independently. And the sharing of information also requires a heavy load on like the network, as well as Wi-Fi capabilities for each robot and the whole environment itself. And lastly, the error recovery management. Like, for example, it executes a particular task and it goes to a place where it's going to do a pallet pickup, and the pallet is not there in that place. So what will the robot do at that point? So all those kind of recovery management scenarios is something that has to be thought before, and then there are a lot of complex algorithms which can be applied to like tackle them. So it can be that it can indicate the nearby user about it, or it can send out an email to somebody, or it can just say, okay, there's nothing here, I'm going to some other place to do my job because I don't want to waste time. So deciding which algorithm works best in order to satisfy a workflow is also like very challenging when we go to like different warehouses. So lastly is mostly the technologies which we are currently developing and using, and most of them I've already covered in this topic, starting with sensor fusion, predictive localization, and obstacle avoidance algorithm. So predictive in the sense that it's going to help us, like, so next time when I come here, I know that something is there, something changed, I update my map, and the next time I come there, I know that that thing is there, even though it was not there during when mapping. So when I mapped, that particular obstacle wasn't there, but now I went 2-3 rounds around the same place, and now I saw something new, so I'm going to add it to my map and say, okay, this thing I can like give a value of, instead of 0 to 255, will give a value like 100, because I've seen it like at least 2 times when I moved around the same place. So something like that. And then the third one is basically parallelizing and multi-robot coordination, which I've also covered. But the idea there is like how well we can make multiple components work together to accomplish a common task, rather than having just one robot doing this point-to-point navigation and task execution. So obstacle map defining is a challenging thing, because if it's like, if we make it like too lenient, it'll be like we will be stopping very frequently, and people will get irritated in a warehouse, because robot is there, stops every 5 meters. Nobody wants that robot. Same way, if it is like not so strict, it just goes very close to a person, that also is not acceptable. So in that case, it's a kind of, we have to work on the accuracy of how well we build this obstacle maps and decide when do we stop and when do we start using it. So mostly we accomplish that by using like some safety triggered sensors itself, because they themselves have safety ratings within them, and they will automatically trigger a safe stop whenever they see an obstacle. So this can be implemented within the sensor as well as within an algorithm in your software application, which can get this information from different sensor inputs and then decide whether to stop or not. And the last and the most important part of the smart HRI is the human robot interface. How are we going to present the information of what the robot is doing or what it's planning to do to the user around you? It can be in the form of like messages in your mobile phone itself. So it can be like, my mobile will move and then it'll give me a message. I am moving from moving package from rack 52 to rack 53, or like something like that. Or it can be like big screens which are there in the part of the warehouses, and it will show each robot moving from one place to the other. And these kind of interfaces are also have to be developed by that company itself, rather than like, I mean, there can be external agencies, but most companies try to develop these kind of external interfaces also in order to like market their products better. Cool. So now coming to my company and what we do. So this is one of the product which we have called the robotic tugger. Okay, this may not work, so I'm going to go out. So this is one of our products which is called the robotic tugger. So this is a vehicle. This is our robot, and it has a hinge at the back and this set of railings. So what it does is that it basically moves.
Ma'am, excuse me, presentation is not there.
Okay, I'm sorry. Can you see now?
No, ma'am. Ah, yes. Ma'am, it's coming.
Okay, thanks.
Yep.
Yeah, so this robot is what we call the robotic tugger, and as you can see, it's like this robot with a hinge, and it actually has a trailer behind it. So the application here is that we have this robot used in industries where we have big packages like this, and these blue are the pallets. They are being assembled on top of these trucks, and the robot actually moves them across the entire warehouse to do applications. So if you see, this is what we call a tugger, which pulls items. And as you can see, there are like different sensors here. Like From the top one, we have some sensors for localization and safety. There's a sensor at the bottom to see the ground plane and understand the obstacles in front of the robot. And similarly, we have some sensors behind the robot and indicators which can be helpful for giving user-friendly interfaces. So this particular light stack is basically going to show, so when the robot is moving, it's going to show that, okay, I'm moving, caution, caution, like move away, things like that. So this is an example of like one of the robots which we have. The other one is the lifter. So this is like a pallet jack. So if you can see here, it's like, yeah, this is like a hi-fi video. So, but the idea is here is doing obstacle avoidance as well as moving around obstacles. So this is what we call like a forklift autonomous robot, which has a fork at the bottom and it has a pallet with a pallet packet on it. So it basically picks it from one place and does the drop off. So yeah, so most of the applications which I have like explained is very similar to what we are developing in my company also. Yeah, so let's go to the last part of the presentation, which is about the future trends in the field of AMRs. And the one of the important thing which everybody talks about now is like artificial intelligence, and everybody wants to use that in their different field. So understanding how to do this intelligent automation from rigid automation. So rigid automation is like everything is like predefined, and then it goes on that same pipeline every time, one after the other. There's nothing new added to it, or no improvements happening, no closed loop processing happening. So the AI here would be to like inculcate something which we have learned from the past into our future decision making. And that's something which is very trending in the field, or it's something which every company is trying to improve upon, including my company, which we are developing something called Pivotal Engine. And what it does is basically it tries to do a predictive kind of motion planning. It tries to understand, okay, for last time I took X time to reach from A to B, following path, maybe A1, B1, B2. And now I'm going to try which other path works out better if I can reduce the time by half. And then try to understand the cost of my path and like predictively gauge it and keep changing it each time it does that same kind of implementation. So here the important part of AI is to understand how we can use our previous decision in order to like influence what the next set of tasks the robot is going to do. And the next part of it is the multi-device interfaces. So now with all these technologies and from smartwatches to smartphone to like all the IoT devices, the people are super interested to have the robot not only work with humans, but also like give information in a more distributed fashion. So if the robot is having any trouble, it can directly send you a message saying, okay, I'm stuck in this place, I need assistance. That time maybe a human can go and interact with the robot and then actually drive the robot. So if you see, each of these robots also allow a manual mode because it's much easier. So anytime it gets stuck in autonomous mode, it can also always be switched to a manual mode and driven around and can be used to do the same task. As well as it can also like give more information in the same of like barcode scanning. So if I have an application and then if I go and actually show the barcode scanning into the robot, it can actually scan it from the mobile phone and then do a particular task. So the multi-device interfaces is something which every industry is looking forward to, and they are like really interested in working through it. So this is some of the references which I took for preparing this presentation. Most of these companies are like Six Rivers, Vecna, Fetch, Conveco. All of them are mostly based in the US, and they're specifically good leaders in the field of AMRs. Yep, I think we're close to 30 minutes left, so I think it's a good time for questions.
Thank you, ma'am, for a very wonderful session. We'll share the questions now.
Sure.
Ma'am, are the questions visible?
Yes, sure.
Ma'am, the first question is from Dr. S. Raghavan. He's a professor at NIT Trichy, and he's also a proud alumni of CET.
Okay. Yeah, hello, sir. So yeah, so DARPA challenge. So that was like it's a very exciting challenge, and this was called the Space Robotics Challenge. So the idea is that we had to develop algorithms for the humanoid robot Valkyrie to do a specific set of tasks. So basically, we had three tasks in that challenge. One was like consider the robot is in Mars, and it has to identify some colors which are coming on the screen, and those colors are like helps it to understand, like let's consider a pattern of letters. And it basically the challenge was the robot stands in a particular place, there is a panel in front of it, and then it shows a set of green, red and yellow colors which come in different pattern and at different times. The challenge was to understand the position of each pattern, each color, recognize the color and write it down into the basically we have to like document the time at which the light was detected by the robot, where that light was detected and what color it was. So it is basically a very basic computer vision challenge, but it also had to like we have to give the correct position with respect to the robot coordinates. So that was the first round of it. The second round was some more into motion planning and control, where the robot is outside the spaceship, and all what it has to do is like turn a wheel in order to open the spaceship door. So in that case, the idea is it's a circular wheel, and then the robot has to actually form a circular motion with its arms. So in that, it was basically a motion planning algorithm we had to design in order to actually move the manipulator, which is the robotic arm, from position A to position B. So that was the second part of that challenge. And I think the final part was even more like very difficult. So our team got into the finals of it, and we came third in the overall challenge. So the last part of the challenge was the robot is inside the vacuum chamber, and the oxygen has suddenly run out of that inside the space shuttle. Now the robot has to go and then open the oxygen valve, which requires it to like cut through one particular wall. So it's basically cutting a particular pattern with a saw. So it has to go and do a picking task, go there and then cut through it, and then pick another equipment out of it, and then move it in a specific pattern in a like through a door. So there are multiple parts of it, like recognition, motion, control, as well as like coordinating different activities together. So that was basically like the DARPA challenge. But so the winner, the person who actually won the challenge, so everybody was like gauged based on the time taken for finishing the challenge, and that's how the winner was decided. So the team which actually came first was having the least number of people. There was like a 5-member team, and they were like very fast, and they were able to do it, and they got the opportunity to go to NASA and actually implement their code on a real robot. So we had to do all these algorithms on a simulated environment, and simulated Valkyrie robot in a gazebo environment is what we call it, using ROS, robotic operating system. That's what the entire the software was used, and gazebo was used as a simulator. But the winning team actually got to go and implement their code on the real robot. Does that answer your question? I think so. Okay. Maybe then I can go to the next question.
Okay, ma'am.
Sorry. Yeah. Should we trust drones with warehouse management? So the idea of drones is that the part is the stability and the control of drones is much more harder than the mobile robots, as you know, because mobile robots are already on the ground. There's no possibility that it can fall off and lose balance. There have been like very outstanding research happening in the field of stability and control of drones, and one of the leading people in the UPenn University, he has a lab which basically specifically works on aerial robots. I think that's even a course on it in Coursera on mobile aerial robots. So definitely there's been a lot of good research happening in order to make them stable to different conditions during pickup, drop off, as well as when they are in the air. But as far as safety is concerned, any warehouse management system, they have very high level of safety constraints, even for a mobile robot like we saw on a ground plane. So ideally, at least current scenario, the like the deployment of drones in warehouses are not something which I foresee. And it's not about like trust, it's just about the risk is much more in that, and people are not ready to take risks on machines so much as yet. Cool. Okay. The next question is about the difference between Industry 4.0 and the Internet of Things. So Internet of Things is basically using smart sensors and smart devices which can integrate. So it's mostly embedded technology, right? So you can design something like using Raspberry Pi. You bring up something which can integrate and record humidity, temperature, and then that sends that information to your computer or your phone or your smart device. So Industry 4.0 is mostly like so like IoT is like a part of Industry 4.0. It's like a subcomponent and it forms an important part of it. But the difference is that it's like a subset. So IoT is like a component, and it has to in turn interact with things like cybersecurity, cloud computing, other robotic other applications, different workflows, and interact together to like accomplish something which is useful for the industry as a whole. Whereas most of the IoT devices which we can develop like small objects within our house, they are like specific for that particular application and may not always interact with so many other interfaces. So that's kind of the basic difference between the two, and the risks for the Industry 4.0 solution. So it's something which is like upcoming and something which people are trying to implement and integrate. They are kind of like already defined mostly what are the different components which we are expecting as a part of Industry 4.0. It's more like a Revolution 4.0, but the risks are not well defined. But if you think about what other risks can happen, definitely like data security is an important part, right? So the more we are getting, so even we know, right, when we buy the smart devices like Alexa or Google Home, it's that we are risking some part of the data we are sharing and what we are communicating. So there's always a part where some part of anybody can hack, phishing, and so many other security risks as well in the software side of things, as well as like in the integration side of things. So sometimes when we integrate also, so one of the most important part, like when we try to deploy robots or any kind of equipment in our industry, is that it should be hack free. Security should be very high. There should not be like open ports, open ended endpoints where people can hit and hack data from it. So that is still a part of, even so as we try to integrate more devices which helps us to improve the connectivity of the device, there is always this risk of things like data loss or data malfunction, manipulation, and things like that. That's what I feel like one of the biggest risks with more integration of these technologies for better connectivity. How to get into the industry of data warehouse management. Okay. So if you're interested in robotics, the most important thing is like to decide which field. So when we saw right now, we saw so many components are there, and they're very important in order to like make a robot itself work, be it sensing, navigation, or workflow. So understanding what you really are interested in will help you at least like define your field in robotics. So for example, I was like, initially I started with computer vision, and I really like computer vision because it helps me to like, it's a very core part of the robot, as well as it understands the environment of the robot around it. But so this particular field again involves many things, like since it involves multiple parts of it, like vision, navigation, if you focus on one of them, it's very easy for you to be like contribute that particular component of a data warehouse field. And once you start working on it and like implementing more algorithms or understanding how it can interact with other systems, gradually it's pretty easy. So getting into the industry is mostly like so I think in India we have Grey Orange. It's a company in Hyderabad which works on warehouse robots. It's pretty famous, and I think it's one of the biggest. Their robots are very robust, as far as I've heard, and they have recently started a branch in Boston also, like from India too. So it's really great. So So if you see the person who started that company, he basically was application driven. So they had this challenge where they had to actually meet a demand. And what will they do? They started with developing small mobile robots within their like it's just like a couple of friends joining together and developing this robot, and then finding a application which is like much larger scale. So if I start like producing many robots of this kind, you can actually do this task. And it need not be that you have to start with a very big product which does everything. It can even be just a point-to-point robot which can do something, and then we can always modify and add more complexities to it. So I think even a small basic college project can actually get into like becoming a change in the industry. So what are the different control systems used in industrial automation? So if you think of like the techniques which we have learned, especially when we learn, we will be like saying, okay, we leave closed loop control system, PID control system. So all of this are very basic techniques, and yes, they are all important and mostly used in all applications. But it's mostly when it's a very low level feature as far as like moving encoders and activators and actuators. That's where we actually apply, and how the robot navigates thoroughly depends on the control system which we implement in it. Most of the error scenarios we tackle by using PID controllers, which are like very simple, and mostly it decides how we want to do. But when we come to like things like dropping off or doing kind of docking approaches, we have like closed loop algorithms which we implement basically for understanding how the trajectory should form when we have a set of points from moving from point A to point B, and then we do like based on the obstacles detected and the cost map, how it looks, we try to align the trajectory with the planned trajectory. So it's kind of error detection and error reduction technology scenario, but the whole thing works on the closed loop. So it's very similar to what we have learned, but mostly when it comes to the application, there are multiple other constraints which come into play, and then we use those constraints to like actually complete our closed loop like control algorithm. Okay, the last question is what is approach indoor GPS solution in warehouse robot? Is there any device that can be used instead of GPS signals for? Okay, so global positioning system is so ideally it's not the thing which we use for indoor navigation, because yes, GPS is definitely very helpful, and I think mostly it's super helpful for outdoor applications because it's going to be in the world, you're traveling from one place to the other and not in a closed environment. So in an indoor application, it's basically from point A to point B, and mostly it's going to be the same point A to point B, or maybe C and D every time, and it's just that particular like consider like some square feet, 500 by 500 square feet area. It's not going to be like across the globe or something. So GPS is not well preferred, and it has some of the disadvantages in it, like getting a good localized, like globally local and locally local. So we have to define where the robot is in the global map or in the local map. So there are some challenges in that when we use GPS. So here what we use is something like we use like localization techniques, which would be by using sensors to actually map the environment, to take different views of the environment, stitch it together to make a map. So it can be just like a normal obstacle detection sensor, which kinds of like gets images in the 2D plane, and then together once we get all those images, we basically map it and form our map, which will be just like a 2D map with different components. So wherever the object actually went and hit and came back, it'll mark it with X, saying that there's some obstacle there, so I can't go there. So that's how we do it. And once it comes back, it gets kind of a closed loop map, and then it can reuse that map each time it travels. So good references would be to like understand like different localization algorithms, and like there's so many techniques which we use for localization, including Kalman filter, and most of this are like used in even aeronautics applications. So it'll be a good step to start understanding. So it's mostly like a probability distribution algorithms, and it involves a lot of math in it, but it's pretty robust to changing environments. Is there any feedback system that can indicate failure in the robot sensor well ahead? Failure in the robot sensor well ahead. Okay, so So I don't know whether you mean by the sensor itself failing or if the detections are not good enough. So if it's the sensor itself failing, it's not like we can predict it well beforehand. But if it's like deciding whether the sensor data is reliable or not, so that is one of the reasons why if you see that most of these new whether it's robots or self-driving cars, they all have multiple sensors. So it's like, I won't say they're like redundant sensors, but they have each have a purpose, and mostly all of their data is being fused to form my final map. So even if one of them is like having a 10% less reliability, the other sensor would be good enough to like actually cloud over that 10% reliability loss to give me information good enough for the robot to move. And we always have this kind of a metric where we say that, okay, I got all this information from all these sensors. Now I decide whether this particular should I move or not, whether particular obstacle exists or not. And it's not like a digital it can be digital also, but it's mostly an analog way we represent that particular obstacle in the environment. And based on that, we actually decide how much we have to move further from the obstacle and how well we can gauge it. And like when you move closer, so it's like a continuous loop, right? We keep always sensing each time the robot moves. It's not like in one position we're going to stop and take an image and then just move. We're going to like keep getting images from it, and then that rate is again important, and like deciding what rate we're getting the images and then processing them. So since we have multiple sensors at multiple positions, we are always like making sure that each sensor will overcome the limitations of the other. But there's always a possibility that one of the sensor can malfunction and can cause like so one of the common errors we call something like a ghost points. So that is like the sensor gives some information of some sparse noise data, and then the robot thinks like something is there, something exists, it's called the ghost point, and the robot just stops because it thinks something is there and it can't move. So how do we like overcome that, right? So one of the things which people think of or they have done in the past is like there's always an interface for you to like work with the sensor. So for example, if I provide the sensor output to a common interface where I'm as a support user, so I have like a network support people in my company who sit and watch the robots every day, like, and then they can control the robot actions through a set of panel, like sending some instructions, and they have one of the functionalities: clear this cost map ghost, clear this sensor ghost. So when they press the clear button, all it does is that it erases that data, because we as a person, I can see it and I can decide that it's not reliable. So the feedback mechanism there is like having an external entity like a human interact with the robot at that point of time to say that, okay, robot, there is no ghost there, so you should just keep going because that sensor was detecting something which is not correct at that point. Okay, next is there any mutually communicating warehouse robots in use? Okay, so most of the current robot systems are centralized in nature. That means there's a central server running in that particular warehouse, and it's the one which gives instructions or tasks to all the robots, and they all work together. Work together in the sense that they do their own stuff, they come back and finish their work. But the mutual communication part, like if you see like inter-vehicle communication, that much is, so the amount of noise can happen due to the Wi-Fi technologies as well as the distance between the robots. So many factors play a role, but the way they mutually communicate in a small sense is like sharing information when they're close to each other. For example, a good scenario would be like a traffic management, right? Suppose there is an aisle and two robots are coming to the aisle. Now, who will go first and turn? It's similar to how we have a real traffic signal, and there are no traffic signals in a warehouse place. So how does the robots actually move? So in that case, that's where they're close to each other. At that point, it's the best way for them to like communicate with each other. So then robot A says, okay, I came here first, so I'm going. So robot B says, okay, fine, you go. And then robot A turns and goes. And then robot B then turns and goes. So in those scenarios where they come in close contact with each other, like on when such decisions are made, that is when it's like a common scenario where currently communication is happening between these robots. I think that's it.
Thank you, ma'am. Thank you very much for a very informative session. So there are no more questions. So we'll wind up the session.
Sure. Thank you very much. Thanks for this opportunity. It was my pleasure.
Thank you, ma'am.
Thank you.
The next session is scheduled at 11:10 a.m. Thank you.
Thank you. Okay. Bye.
Good morning, sir.
Good morning.
So we'll start the session shortly.
Sure.
Welcome back. Now we are entering the second technical session of today, which is based on programming robots using ROS by Mr. Lyndon Joseph. Mr. Lyndon Joseph is an author, a roboticist, and a robotics entrepreneur from India. He runs a robotic software company called Cubotics Labs in Kochi, Kerala. He has 10 years of experience in robotics domain, primarily in robot operating system, OpenCV, and PCL. He has authored 8 books in robotics, namely Learning Robotics Using Python, first and second edition, Mastering ROS for Robotics Programming, first and second edition, ROS Robotics Projects, first and second edition, and Robot Operating System for Absolute Beginners. He has pursued his master's in robotics and automation from India and also worked at Robotics Institute, CMU, USA. He is also a TEDx speaker. Now, I hand over the session to Mr. Lyndon Joseph.
Okay, so good morning, everyone. Thanks for the introduction. So today we are going to discuss about robot operating system. Okay, so I used to ask questions to you. So you can use the raise hand option in Google Meet. So the first question is, how many of you heard about robot operating system before? You can use the raise hand option if you already heard about robot operating system. Anyone? Are you hearing? How many of you heard about robot operating system? Okay, one. Great. Okay, only one. Okay, fine. So, so in this talk, I'm planning to give an abstract idea of robot operating system. Okay, this is actually a very big subject. Okay, so in this 1.5 hour, I'm trying to give an abstract idea. Okay, with some examples. Okay. So again, I just want to introduce myself. My name is Lyndon Joseph, and I'm running a consulting company, robotic software development consulting company called Cubotics Lab. And I used to write books in ROS. Okay, till now I have authored about 8 books, and I'm working with robotics from 2010, so 10 years of experience in robot and ROS programming. Then I used to write blogs in my blog called Robo Academy, and I have worked in CMU. Then I have done masters in robotics and automation. Then I also spoke in TEDx. Okay, so these are some of my experience in robotics domain and ROS platform. Okay, so let's start. Initially, I just want to show you some books that I have written: Robot Operating System, Absolute Beginners, Learning Robotics Using Python. And these are some of the books, Mastering ROS for Robotics Programming. So these are some of the books, and these are some of the books that I reviewed. I didn't include all the books, and almost all the books are related to robotics, Raspberry Pi, computer vision, those kind of stuff. So this is the agenda that we are going to discuss. So initially, we will start with some basics like robotic programming, those kind of stuff. And it will not take much time. And after that, we will come to the introduction of ROS. Okay, so we will see, let me check my pen. Yeah, so we will start with installing, then some concept. I will be showing some examples, and I will be, at the end, I will be showing some video demos based on our time. I can show. And importantly, what are the things that you are going to get if you learn ROS? Okay, and at the end, we can do a Q&A session. Along with that, I can show you some simulation demos. Okay, so this is a plan, and let's see how it goes. Okay, so we can start with robot and robot programming. That is the first topic, so it will not take much time. I will quickly go through it. So I'm using Ubuntu 20.04 and ROS Neutic for demo purpose. Okay, so the Ubuntu distribution, I'm using the latest one, and the ROS distribution I'm using is ROS Neutic. Okay, let's start. So what is a robot? Simply, I think you guys know about this, but I'm just saying it again just for refreshing. So robot, it is having 3 blocks. Okay, so first block is sense, then second block is think and act. Okay, so the sense block is having a list of sensors like camera, lidar, then ultrasonic sensors, those kind of stuff. Then in the think part, it's actually the computer unit. Okay, so it is taking the decision based on the sensor input. Then the act part. So basically the robot is doing some actuation, okay, based on the motors. Okay, so in the act part, it is having a set of actuators. Okay, and this is the robot feedback loop. I will say, like, this is a physical robot. Okay, and from the robot we will get the sensor reading. Okay, and these sensor readings are processing by a control computer. Okay, and the control computer will generate the control signal and its feedback to the physical robot, in which it is having the actuators, so it will move that actuators, and the robot will move. Okay, and this is a very simple sense, think, act loop. So you can see the sense unit is sensing the environment. Here it is an example of an obstacle avoidance robot. Okay, so the basic purpose of the sense unit is sense obstacle, right? So here the sensor is saying, hey, there is a wall, it's 5 centimeters away from me. Okay, it didn't detect as a wall, but hey, there is an obstacle just away 5 centimeters away. Okay, so that control signal is sending to or the sense signal is sending to the think part, and think part is taking the decision. So it will take a decision like, oh, it is too close, so should I move away or not? Okay, so if it is too close, then it will send a control signal to the actuator part. So the actuator part will move the robot, okay, away from the obstacle. Okay, so this is a basic sense, think, act loop. So you can see this loop in all robots basically. Okay, so if you take a simple robot or if you take a complex robot, you can see these blocks. Okay, so this is a much detailed block of a robot. Basically, like, the actuator is having list of actuators, then sense, and the important part that we are going to discuss is the think part. Okay, so think, as I mentioned, it is having the computers, right? So either it may be a full-fledged PC, or it may be a single board computer like Raspberry Pi, or it may be a microcontroller like Arduino or STM32, like that. Okay, so we are going to focus on the think part, guys, because we are actually going to program the robot, right? So the program is actually putting in the think part that is in the computer. Okay, so these are the main components of the robot again. Like, I just put some examples for sensors. I can show you that. So some of the examples of sensors are camera, wheel encoders, ultrasonic sensors. Then some of the examples of actuators are servos, stepper motors, DC motors, etc. Then computers are like, we can use a laptop as a processing unit, or there are some single board computers like NVIDIA TX2, NVIDIA Jetson Nano, then Intel NUC. These are the platforms that we can prefer to put in the robot. And also we can use the microcontroller platforms like Arduino, Texas Launchpad, ARM controller based boards, those kind of stuff. So these are some of the examples for the actuators. So you can find the RC servo motor here, stepper motors, DC gear motors, industrial servo motor. These are using in industrial robots, industrial manipulators. Then dynamical smart actuator. This is very expensive servos, which is mainly using for research. Okay, so yeah, these are some actuators, and these are some famous sensors. So if you had about self-driving cars, those robots, actually that is a robot, right? So those robots are using these sensors. It is a LiDAR. Okay, it can give you the 360-degree 3D view of the environment. Then this is a laser scan. This is a depth sensors, which can give you the depth information of the environment. And these are some basic sensors like ultrasonic, sharp, distance sensor. And these are some of the computer unit that I mentioned: Raspberry Pi, then industrial PC, Odroid, NVIDIA TX2. So these things belongs to the single board computer, meaning it is having a single board with a, very small form factor, very small size, which is having an SoC, system on chip. Okay, will be inside the one. Okay, it is having an SoC, so that is having processor, RAM, then GPU, all the stuff. Okay, and this is Intel NUC, which is like a desktop computer, but which is having very small form factor. Okay, so these are some of the information about the Sense Think Act units. Okay, so now we are going to the robot programming. So we have seen what is a robot, basically, what are the main components that we are using. Now we are going to discuss about robot programming, right? So it's not again complex, guys. Like simply a robot programming is this. Okay, what we are basically doing is we are modeling the behavior of the robot. Okay, using a programming language. So if you take the computer, we are saying computer programming, right? So basically we are doing some kind of input from the input device, and we are putting some output in the output device, right? So that is the computer programming. Similar to that, if it is a robot programming, we are actually modeling the behavior of the robot. Okay, for example, in case of an obstacle avoidance robot, the behavior is that if there is an obstacle, then the robot will should move away from the obstacle, right? So that is implemented using a programming language. Okay, so we are basically modeling the behavior of the robot using a programming language, and that is called the robot programming. And the input of this model is robot sensor, and output is the robot actuators. Okay, so the actuators is executing the output from this model. And commonly, we are using the programming language like C++, Python in order to program a robot. Okay. Yes. And these are the two different approaches that we can use in order to program a robot. It's again very simple. Like, so you can use an existing software framework to program a robot. Okay. Or you can create everything from scratch. Okay. So in this session, we are focusing on the first method, that is, we are taking an existing software framework, okay, and we are using those frameworks to program a robot. Okay, so one of the existing framework is robot operating system, okay, and using this framework, you can program robots. Okay, so what is the advantage of that? The good thing is that it will not take much time to program. I think somebody's mic is on. Can you just mute?
One sec, sir.
I think somebody's mic. Okay, okay. Yeah, can you just mute them? Okay. Yes. So the first method is, use existing software framework. I think that mic is still not mute. Let me check.
So now it's okay. Is it okay?
But I'm hearing some background noise. I'm not sure from. I think it seems like all the microphone are muted.
Sir, everyone is muted.
Okay, okay, great. Yeah, you can also mute. Yeah.
Okay, sir.
Okay. Okay, fine. So we've been talking about the software framework. Okay, so in order to program a robot, you can either use a existing software framework like ROS, or you maybe heard about Arduino framework, right? That is for programming the microcontrollers. So that is again a framework. Okay. The second method is that you can use a programming language, simply maybe a C, C++, Python, or any programming language to program a robot, okay, from scratch. Okay, so that is again the second approach. So the problem is it will take a lot of time, but if you're considering a product or something, then it will be good in long run. Okay, so we are going to discuss about this method. That is, we are taking some existing software framework and program. Okay. But if you are doing it for a product, then it may need a lot of fine tuning, because it's an existing software framework, and in order to make a finished product, you may need to fine tune. Okay. Okay. And these are some of the existing software framework for robots. Okay. So sorry for that. So we know about robot operating system. We just know there is a thing called robot operating system. Then there is another framework called OpenCV, Open Source Computer Vision, which is mainly for the computer vision application. Then there is PCL, that is point cloud library, mainly for the 3D point cloud processing. Okay, and as the name suggests, robot operating system, it's not a real operating system. It's called the meta operating system. I will come back to that. Okay, and these are some of the free robot framework available. This is called a robot simulator called Gazebo. Okay, this is actually coming along with ROS. So using Gazebo, you can simulate the robot, okay, virtually. And there is another framework called OpenRay, which is like for motion planning, and those kind of stuff can be done using this. Okay, this is again some of the free simulators available. Maybe you can suggest to your students or something, WebBots, VREP. So these are very user-friendly robot simulators. Okay, and these are some of the famous programming language that we are using for programming robots: C++, Python, Java, C#, MATLAB, of course. Okay. Okay, so another question is why we need an operating system in robots. Okay, so I think you may have seen this kind of robot, the simple line follower robot, obstacle avoidance robot. Maybe in your college or something, students may be doing some prototyping like this, right? So is there any computer or is there any laptop that is mounted on the top of this robot? No, right? There is no computer or something, but it may have some digital circuits or a microcontroller, right? So these type of line follower obstacle avoidance robot may be working using a digital logic circuits or simply a microcontroller, right? So we don't need an operating system like Windows or Ubuntu for working with this. But consider these robots. These are much complicated than this line follower robot. This is having two arms like ours. Then there are some sensors, right? So this looks very complicated, right? So in this case, we may need some computers in order to do the processing of the sensor data. Like in case of this robot, it is having stereo camera, then laser scan, all this stuff. So we may need a computer in order to process this heavy sensor data. Okay, so in that case, we will be connecting this sensor to a computer. Okay, and there will be an operating system inside that, and that is doing all the processing. Okay, we have to write programs, maybe in C, C++, or Python. You have to write programs, and we have to process, and we have to send the control signals to some actuators. Okay, so this is a case of a complex robot. Okay, yeah. So these are some of the operating systems that we are using in robots. Ubuntu we are using extensively. Then Debian, again, Linux variant. Rarely we are using Windows and Mac OS. And for your information, if you are doing some real-time tasks, then we are using QNX and VxWorks. These are very famous real-time operating system. Okay, so let's start with the ROS thing. So in order to start with ROS framework, we may need these skills, that is Linux terminal commands, C++ or Python. Okay, so you may need to know the Ubuntu basics, Linux basics, and also some terminal commands. Okay, so these are the prerequisites to start with ROS. And also you should need some programming experience with C++ or Python. Okay, if you have these, then you can work with ROS. Okay, so let's start with ROS. So I would like to say an example. So this was one of my project that I did in my bachelor's. It's called a social robot. Okay, so the objective of this project is this robot can interact with people through vision. It can mimic the gestures and so much stuff. Like it can talk to talk to people. It can communicate like Siri. So these kind of stuff I implemented. This was done in 2010. Okay, and this is me. And when I work with this complex robot, I will say it's a complex robot because there are a lot of things working inside this robot. I have used 2 laptops to process the information, and these are some of the capabilities like speech recognition, face detection, motion detection, all this stuff. So at that time, I didn't use ROS. Okay. I didn't know about the ROS framework when I worked with this. So what I did was I implemented a server client architecture in my program. Okay, and this was the architecture. So I implemented a server client architecture. I think you may heard about the server client. There is a server and a client program. So both can able to communicate. Okay. So here in my case, there is a server program and these all are client programs. Okay. And each client programs can send some information to the server and server can also send information to the client. Okay. So during this project, I have faced these difficulty. Like I need to make a communication protocol. Like there are several programs are running in 2 laptops. Okay, so it's not only one program, several programs. Okay, maybe 5 to 10 programs running in both of the computers. So I face challenges in implementing inter-process communication, meaning communication between different programs. Okay, then synchronization of robot task, modularity, reuse of the code. Then it's very difficult to create an application on the top of my application. Okay, so these are some of the challenges that I faced during my first project. Okay, so main headache was the inter-process communication, that is communication between 2 programs. Okay, so I implemented a server client architecture at that time. Okay, then in 2014 I created another robot for food delivery. It's called Chefbot, and it is having these computers like Intel NUC, then some embedded boards, Kinect, that is a depth sensor. So at that time, I have used ROS. Okay, so the main advantage is that I could like rid of all these issues because using ROS, I can easily implement the inter-process communication. Meaning, if I write a program using ROS framework, okay, then I can easily send message across 2 different programs. Okay, because in a complex robot, you may have to run several programs in your computer. It may be 10, it may be 100, or even thousands of programs has to be run parallelly. And sometimes one program has to communicate with other program. Okay, so that's where the use of ROS comes in. Okay, so using ROS functions, you can easily implement these programs that can able to communicate with each other. Okay, so I'm only emphasizing on the first, and also all these things can be solved using ROS. Okay, so now what is ROS? So ROS is an open source robotic software framework. Okay, so that means its source code is open. You can see the source code, and it's also free. Okay, so free of cost meaning. And basically, it's not a real operating system, meaning it's not an operating system like Windows or Linux. It's mainly called middleware. Okay, I'm not sure you heard about middleware. How many of you heard about the term middleware? Anyone, guys? You can just press the raise hand option if you heard about the middleware. Anyone? Okay, yeah, great. So one person, yeah. So middleware is actually a program, okay, a set of program which is acting between software, the operating system and the user application. Okay, for example, if we are writing a hello world program, okay, and if you're using the middleware is acting between the OS or operating system is there, right? It may be Windows or Ubuntu or something, and if we write our hello world application, that is our user application, right? So the middleware is acting in between. Okay, so ROS is a middleware. It's a communication middleware. Meaning, using this middleware, you can easily establish the inter-process communication between 2 programs or multiple programs. Okay, so imagine you are writing 100 programs in your computer. So 100 programs are running on your computer, okay, in parallel. So using ROS, you can establish communication between any of these programs. Okay, so that is called, that is the main function of ROS. It's a communication middleware. Okay, so this program, this set of programs will help you to establish communication between different programs in your computer. And ROS is not a real operating system, so it needs a host operating system to run. Meaning it may need Ubuntu, Windows, or some other operating system to run. Okay, so I would like to show you the website of ROS. Okay, so if you can just go to ros.org. In between, there is a question, sir, which one is good for robot, single board computer, or a small PC? So this was one question. So it's according to our application. So choosing the computer is based on our application. So if the processing is low, then we can go with the single board computers like Raspberry Pi and all. But if you are doing a lot of processing in your robot, then I think small computers like Intel NUC will be fine. Okay, so again, I'm coming to the ROS website, guys. So this is a website, official website of ROS. So you can find there are a lot of options about ROS, then why ROS, getting started. Okay, so in the about menu, you can find about ROS. Okay, and in that you can see the equation, ROS equation. Then in the getting started, you can see the install option. Okay. Okay, so we will be seeing these two options. Okay, I just want to show you the official website. So this is having a lot of information. Okay, about ROS. Let me just move this to here. Okay, so we have seen the official website, guys. Now we are just discussing how to install this ROS in your computer. Okay, so I said you may require a host operating system like Ubuntu in order to work with. So if you're planning to install Ubuntu on your system, you can either install Ubuntu on your real system in your laptop, or you can use some VirtualBox. Okay, VirtualBox or VMware. I can show you how I am using Ubuntu. So here is VMware. And here is VMware, and I install Ubuntu, and I have ROS installed in my Ubuntu system. Okay, so this is called the virtual installation. So just go to Google and search about VMware or VirtualBox. Maybe I can give you the tag. Just a second. VMware or VirtualBox. So this will help you to install Ubuntu by working from Windows. Okay, so you need Ubuntu for working for ROS. Okay, this is a fully supported operating system for ROS. Okay, and the latest one that we are using is Ubuntu 20.04. Okay, and the latest distribution of ROS or latest version of ROS that we are using is ROS Neutic. Okay, so let's see how to install this. Okay, so I am assuming that you have Ubuntu installed on your computer. Yes. Okay, then you can just navigate to the ROS Neutic. This is the latest version of ROS, and just before that there is ROS Melodic. So just press the install button. You can find the installation instructions. Okay, so it's very simple. Maybe I can show you that. What you have to do is, if you're working from Ubuntu, then take your terminal. Okay, this is a terminal application. Okay, and from your browser, let me take the browser. Okay, so these are the installation instructions, right? So they have put some commands here. So from here, so what you have to do is just copy paste, okay, and paste it here. Okay, just do it. I already installed ROS, so I'm not showing it. So it's very simple. Just copy paste it. The first, then here is where we are installing the full packages of ROS. Okay, So this is the method for working with, how to install rows. So I also have written a blog relating to that. Maybe I can share that also. So that is having tutorials of how to install rows using a single command. So there is a video also. You can just have a look. Okay. So that is about the installation, guys. You can just go through this procedure and just copy paste this command on your terminal and it's ready to go. Okay. So it's not very difficult. So that is installation. And after installation, what you can do is, in order to check, in order to verify the installation is correct, you can run any rows command. So I am running a command called rows core. And if that is working fine, then I can assume that Noitic is working, rows is working good. Okay. Yes. So if you have any doubts, you can just post it in the chat box, guys. Okay. That would be good. So if I can check the chat, I can understand the questions. Okay. So this is the installation procedure, guys. Now let's move on to the equation. Okay. So this equation we have also seen in the about page in rows, right? Let me take that page. Yes. Okay. So in the about page, you can find this equation. Okay. Let me explain what it is. Okay. In a simple way. So we have 4 things in rows. Okay. The plumbing, tools, capabilities, and ecosystem. Okay. So plumbing is the part that I am focusing on. This is the middleware that I am talking about, the communication middleware. So I already explained the use of this middleware. The objective is that using this middleware functions, you can able to establish communication between 2 or more programs. Okay, 2 or more programs. It may be, if you are writing an application called Hello World, you can create or you can able to establish communication between 2 programs that is running. Okay, and you can send data, send or receive data. Okay, so this is a main part of rows. Okay, plumbing means it's like the inter-process communication. Okay, then it is providing some tools. Tools means some software application, like some visualization like this, in order to visualize the sensor data and in order to debug the robot system. Okay, I will show you the list of tools. Then it's also providing some capabilities. This is interesting part. So imagine you have a mobile robot. Okay, and you have to make this robot autonomous, meaning you have to move the robot from A to B without any manual intervention. Okay, so that is mean autonomy, right? So these kind of things can be easily implemented using rows capabilities, because these capabilities are already there in rows, us rows packages. Okay, so you don't need to work from scratch. You can simply take this package and customize it. Also, if you're working with this arm manipulation, like inverse kinematics, all this stuff, then there is a package called Move It. Sorry for that. Move It. So you can use those packages in order to implement inverse kinematics or motion planning in robotic arms. Okay, and after that, there is an ecosystem, meaning there are a lot of developers in rows. Also, it's an open source project, right? So a lot of developers are contributing to this project, and yeah, so there is a very well established ecosystem around ROS. Okay, so this is something that I explained, and now let's see some examples of inter-process communication. Okay, so basically, inter-process communication means communicating between different programs. So here is our computer layer. Here is the OS layer, and here is the rows. Okay. So using rows, you can use the rows functionalities to write our programs. So here we have program 1, program 2, and program 3, and like these programs can communicate with each other using the rows functionality. Okay. Okay, so this is a practical example. I will show the real examples, I mean demos after this. So this is an example for the face detection in rows. So we have one program here which is reading the images from a camera, okay, and it is sending that camera images, okay. And there is another program called face detection program. So that is basically receiving these camera images, okay, and it is doing the face detection. Okay, so after doing the face detection, this program will send the data, that is the centroid of the face, to another program. So this program will receive the centroid and send to some Arduino board or something. Okay, so this is one example. So you can see the inter-process communication 1, 2, 3. So there are 3 programs, and 3 programs are simply communicating by exchanging data. Okay, so let's see the working of rows communication using some examples. So before that, I just want to clarify, like, so we have the robot here, okay, and in robot you can put some computers, okay. On computer we may have OS like Ubuntu or something. Then on the top of Ubuntu you can install ROS, and on the top of ROS we can install or create a robot application. Okay, so this is the thing. So we are creating applications here, your programs, the application means your programs, and which is using the ROS middleware. Okay, so ROS is providing some API or application programming interface or some functionalities to our programs, okay, in order to establish the communication. Okay, so this is the detailed view. So ROS can be divided into 2. So the middleware is there, and it's also providing an interface to program the middleware. So you can use C++ or Python, and there is functions. So you can just include the ROS header files or modules, and you can use the ROS functionality in your application. So this is important part of this talk. Okay, so that is the ROS concepts. Okay, so basically I just want to show you this diagram. Okay, so basically you can find there are 6 programs that is running on your computer. Okay, so program 1, program 2, program 3. So I just copy paste this thing. So I think it's 7 programs. Okay, so these elliptical structures, ellipse is basically a program, okay, or running program. It's called the process. Okay, and you can find these programs are communicating with each other. That's this arrow. Okay, and it's exchanging some data. Okay, so here the program 2 is communicating with program 5, and program 5 is communicating with program 4. Okay, so guys, do you identify this structure? This is basically a graph, right? Okay, so this is having nodes and these connections, right? So in ROS terminology, we are calling it as a computational graph. Okay, so this is important terminology in ROS, guys. So this each ellipse is a program. Okay, and these programs are communicating with each other using ROS functionalities. Okay, and basically what it forms is that it forms a graph. Okay, graph of nodes. Okay, so each program is doing some computation. Okay, so basically it's forming a computational graph. Okay, I think you have understand the concept. Using ROS, we are actually trying to create a computational graph, meaning there will be several programs running, and all programs may be communicating with each other and exchange data. Okay, so this is a main concept of ROS. Using ROS, we can create a graph of process. Okay, each process is doing some computation. So so in order to work with this computation graph, we have some terminologies. Okay, for example, we are calling these programs as nodes. Okay, just renaming the programs to node. Okay, so ROS node is basically this ellipse structure. Okay, so that is the first terminology, that is nodes. Okay, and second, you can see each node is communicating with, maybe 2 nodes or 3 nodes, that you can decide. Each node can communicate with any number of nodes. Okay, so this is a communication. Okay, this indicates the communication, and it's exchanging some data, right? Some kind of data, and these data is called rows messages. Okay, the type of data it is sending is called the rows messages. Okay, and there should be some data bus in order to send this data, right? So this arrow indicate there is a bus. Like if you check the NH47 or NH17, using this highway, national highway, we can drive the vehicles, right? So the data bus indicates that using through this data bus we can pass the a type of data. Okay, so when you start establishing connection between 2 nodes, basically we are creating a data bus, and using that data bus we are sending a type of data. Okay, so this data bus in rows is called rows topic. Okay, so we have seen rows nodes, which is basically the programs. We have seen the rows message, that is a type of data it is sending. Then the rows topic, basically the data bus, okay, in which the data is sending. So these are the 3 important concepts that you have to learn, okay, from this computation graph. Okay, so the rows nodes, rows topic, then rows message. Clear? Okay, so we will discuss rest of the things after this. So I mentioned, right, the rows topic is basically the data bus in which one node can send the data to different nodes, okay, by establishing a data bus. Okay, and through each data bus we can send a unique type of data. It may be a string, it may be an integer. Okay, that data type is called rows message. Okay, yes, and we will come back to that. I'm just skipping it. Okay, so now we have seen rows topic, rows message, rows nodes. So now let's see how the communication happen in rows. Okay, so this is the interesting thing. Let me show you a demo. Okay. Okay. So in this demo, I'm planning to show you the communication between 2 programs in rows. Okay. So first I will show the demo, and after that I will explain. Okay. So in rows, we have seen we can able to communicate between different programs, right? So in order to do that, first there is a program called rows master. Okay, so this rows master is like a broker. Okay, I think the better explanation is that in an arranged marriage we will have a broker, right? The broker may be a matrimonial side, it may be a real person. Okay, so what is the purpose, what is the objective of this broker? It's basically connecting the boy and girl, right? So the broker is having details of the boy as well as girl, and if there is an interest or if there is any match, then the broker will exchange the information to both parties, right? So then the communication will start between these parties. Then is there any need of broker? No, right? So similar to that, the rows is having a broker system. Okay, basically this broker is helping different programs to communicate with each other. Okay, so we have a command called rows core in rows. Okay, so if you just start this program, then the broker program will start. Okay, the broker program also called rows master. Okay, so in the rows ecosystem, the broker program is called the rows master, and now the rows master is up, and now we can start the boy program. For example, we are don't worry of the command. I'm just starting a boy program called talker. Okay, so boys are like, let's say it's a girl program, because girls are like used to talk very much, right? So here is a girl program called Talker. So Talker is starting talking. Okay, so it's just started, and here is a boy program. So boys always listen. So listener program. Okay. So what is happening here? You can just see what is happening is the girl program send it's actually sending something, okay, and the listener program is receiving the same. Okay, and let's see what is happening when we start listening to the
Hello, sir. Sir. Hello, sir. 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 It seems there is a technical difficulty at the
yeah,
origin.
now
Sir?
it's fine, I think.
Yes,
Yes,
sir.
yes.
Yes.
Actually, I think there is some issue with my internet connection. Sorry for that. So
Oh,
can you see my screen now?
it's
Is it
not
fine?
this. No,
Oh, okay, okay.
not
I will
this,
share
sir.
it. Yeah, yeah, I will share. I will share. Sorry for that. Actually, I'm not sure like this network issues. I'm
Yes.
presenting it. What about now? Yeah.
Yes, sir.
Okay.
Yes.
Great, great. So we have been talking about the boy program and girl program, if you remember. So boys always listen and girls always talk. So here is actually happening inside inside rows. Okay, so this is a computational graph. Here is the talker program. Okay, and here is the listener program. And you know the elliptical structure is a program basically. Okay, it's a program. It's a rows program. And talker is sending something to the listener. Okay, and listener is just receiving it. Or in rows terminology, we will say talker is publishing something and listener is subscribing. Okay, and the chatter is the rows topic or data bus. Okay, so basically talker is sending some data to listener over a database called chatter. Okay, and what it is sending, it's sending some string data. So what is a rows message type? It's a string. Okay, so this is what happening in this hello world example. Okay, so so what just happened was we just started the broker program, then we started the girl program and boy program. So broker have seen some matches between this, because the talker program is publishing a topic called chatter, and listener program need the same topic. Okay, so then there is a match, then it will start establishing the communication. So I will show you I will explain the working from the slide. I just shown you the demo. Okay, so this is the explanation. I mentioned about the master program or the broker. Okay, and the first step to start rows programs is that we have to start the rows core. Okay, because this is the broker program. Okay, so without the broker, no communication will take place. Okay, so this is a case of arranged marriage. For the love marriage, the case is different, but this is like kind of arranged marriage. So we need the broker, and here it is, the talker node. Okay, so we started our node called talker. Okay, so what the talker node does is that it will contact to the broker. Okay, so hey broker, this is my information. I have masters. I have done this much of things. I have this much of money. So this talker node is communicating this detail to master. Okay, then again the girl comes in. Okay, so I'm just exchanging boy and girl here. So the listener node is girl. So girl is like again exchanging the information like, hey, I have this much of degree and I am very fair, those kind of thing. And she shares the information to the master. Okay, so now master find some match. Okay, the thing is that talker is having some some capabilities, and also listener is having same expectation. I think talker is sending something and listener is expecting the same. Okay, so if the expectation and everything is matching, then the master is giving the information to one participant. Okay, okay, so in this case, in the case of Rose, what happening is that talker is sending a data. Okay, and listener is expecting that data. Okay, so if there is a match, then the master will initiate the communication between two nodes, and now they started find each other, and now there is no need of master. Okay, there is no need of the broker. Okay, now these two nodes can find each other and they can send message. Okay, maybe WhatsApp, Facebook, anything they can choose. Okay, so this is what happening. That is, talker is sending some data, and listen. If the listener is expecting the same data, then the master is exchanging the information between two parties and start the communication. Okay, so this is what happening in background. This is what happening in the Rose communication. So we have seen this example, talker and listener. Okay, and let me show you some more demos. Okay, so you will get clarity. Okay, so now I'm starting a simulator. So the first thing I have to do in Rose environment is Rose core, that is starting the master program or broker program. Now I'm starting a simulator. I will explain what it is. Okay, so this is a simple simulator. So let me take the screen. Sorry, the slide. So how many of you heard about the logo programming? Anyone heard about logo programming? Just raise your hand if you heard about logo. No one? Are you hearing, guys? Okay, okay, great. So if you heard about logo programming, this is like this is intended for kids actually. Okay, so basically for teaching programming. Okay, so it's a very simple programming language. So you can see it's using a turtle, right? It's using a turtle for programming. Like you can just give the commands and the turtle will move. Okay, so in order to learn Rose, we have a thing called turtle sim. Okay, it's very similar to the logo logo programming. So the idea is to learn Rose, we can use this simulator. Okay, the idea of logo. Okay, so this is a Rose program. Okay, and it's basically having a turtle. Okay, so we are saying that turtle is a robot. Okay, and you can move this robot. Okay, so let me show you the demo first, and after that I can explain. Okay, so the demo is basically like I'm starting a program in which I can move this turtle. Okay, you can see the turtle is moving. Okay, and I'm moving this turtle using my keyboard arrow keys. Okay, so what is happening here? Like there is one program running. This is the turtle simulator, and we have another program called teleop key. So I'm running these two programs, and what is happening in the background? Let's check. So this is what happening in background. Okay, again, two programs are communicating with each other. So here there is turtle sim. Okay, turtle sim is this program. Okay, and here is teleop turtle. Okay, that is this program. Okay, and these programs are communicating with each other over a topic called command velocity. Okay, so this is the computational graph of current process. Okay, so there are two nodes and one topic, and basically the turtle teleop node, what it does is that it will listen to the keyboard, and if I press the keyboard, then it will send some linear and angular velocity to the turtle. So in order to move the robot, if you want to move a mobile robot, you have to give the linear and angular velocity. Linear velocity means the velocity to move the robot in a linear fashion. If you want to rotate the robot, you have to give the angular velocity. So basically, this node is sending some linear and angular velocity to the simulator, and simulator is expecting that command velocity, okay, that velocity, and it will move the turtle. Okay, so this is the internal working of this. Okay, basically two programs are communicating with each other. So I just want to show you that how these things are working. Okay, okay, so that is one example. Let me take the slides again. Yeah, so this is a demo. Like, in order to learn ROS concepts, you can use a simulator called Turtle Sim that is already in ROS. Okay, the basic idea is like how the ROS communication is working, what is ROS topic, what is ROS message. In order to learn this stuff, ROS is having this simulator like logo programming. Okay, yeah. So we have seen these things. Okay. Yes. So this is something that we have seen, and now I'm showing you a real world example. Okay. So then you will get a clarity. So here I'm using a mobile robot, actual mobile robot. Okay. It's a very simple robot, but I am showing how to control this robot using ROS. Okay, so we have seen this communication, two programs are communicating with each other. So how can we apply this communication concept to a real robot? Okay, so that is the next thing. So here in this mobile robot, there are two wheels, guys. Okay, and there is a caster wheels on the front, and here is some battery. I can show you the actual structure. So this was the actual structure that I prototyped. So you can find some Arduino boards here, then motor driver, ultrasonic sensors, all this stuff. Okay, so this is the wiring of the robot. We have, in this robot, we have a Arduino Mega board, okay, which is a microcontroller board. And in the this board is communicating with a H-bridge circuit. I hope these are clear to you that this is a motor driver. So Arduino Mega can control the left and right motors using an H-bridge. Okay. Now there is a Bluetooth module. Okay. So in order to send commands from the computer, we have a Bluetooth module. Then there is an ultrasonic distance sensor to detect the obstacle, and there is encoder, left and right encoder to find the speed of each motors. Okay, so this is a circuit of this robot, and this is a software software blocks using ROS. Okay, so the basic objective of this robot is that dead reckoning, meaning if I give a position that is XY theta, then the robot should move to that position. Okay, so how I achieved was I used ROS. Okay, so basically these blocks, right? These blocks are each programs. Okay, each programs, and this is the hardware. Okay, this is a robot that we are talking about, and these things are running on the PC side. Okay, and this is a robot. Okay, so what's happening is that a robot is connected to a Bluetooth module. Okay, so a robot is having a Bluetooth module, right? So that is connected to PC, and it exchanging the data from sensors. I mean, a robot is having sensors like encoders, ultrasonic sensors, those kind of things, right? So robot is sending these data to PC over Bluetooth. Okay, and also the PC can send the control signals to robot over Bluetooth. Okay, so there is a ROS Bluetooth driver which is using ROS API, and you can find all these nodes are communicating with each other. Okay, so this is where we are using ROS. If we have multiple programs and if they want to communicate with each other, then you can use ROS. Okay, so here I'm giving an XY theta position from a tool called RVs. Then it's going to dead reckoning node. Then it's sending the linear and angular velocity to twist to motors node. Then it's sending to the Bluetooth driver. Okay, so these communication is establishing through ROS. Okay, I just want to show you the communication diagram. I'm not explaining in detail. So I think you guys understand like where we can use ROS. Where if we are using multiple programs, then if you want to establish connection between these, then you can use ROS. Okay, clear? Okay, so if you have any doubts, let me know in the chat box. Otherwise, I'm moving to the next topic, that is ROS tools. So I can show you what is ROS tools and ROS navigation. So these are interesting topic. If you have any doubts, just post in the chat box. Okay. So the next topic is ROS tools, guys. So I can show you the demo first. Okay. So I'm starting some ROS tools. Okay. So this is actually a ROS tool that is ROS providing us. So basically, ROS tools are for visualization and debugging. Okay, so if you want to visualize a sensor data or if you want to visualize a robot model, you can use ROS tools. Okay, so there is another tool called RQT. So one of the famous tool is RVIS, that stands for ROS Visualizer, and we have the RQT, which is a 2D visualizer in which we can use it for debugging the system. Okay, so these are two tools basically for debugging and visualization. You can find the visualization of robot in RVIS here. Okay, and this is RQT. Okay, we will see these tools during the demo. Okay, and these are the important things. The capabilities. So we have seen the plumbing part, that is the inter-process communication. Then we have seen the tools. Then we are going to see the capabilities. Okay, so capabilities means if you want to make the robot autonomous, then you can use the ROS navigation. If you want to make your robotic arm, if you want to implement the inverse kinematics, you can use ROS move it. Okay, so I will show you a video. So this is a video showing how to make a robot autonomous. Okay, so you can see the robot is path planning. Okay, I'm giving a goal position and the robot is autonomously moving from A to B. Okay, so this is ROS navigation. Okay, so using ROS navigation stack, you can implement these kind of capabilities in your robot. Okay, and also I just want to show you the ROS manipulation. Okay, so it is having the audio volume is very high, so I can show you that. Let me take that and mute. Yeah, let's watch this video. Okay, basically it is showing the ROS manipulation, guys. So basically this robot is taking this block. Okay, you can see this taking this block and putting on the top of that platform. And you can see in the monitor, you can see the RVIS, that is a tool, ROS visualizer. okay, and it's taking another block and it is putting on the top of the block. Okay, so these things can be done using the help of rows move it, okay, which is a capability in rows. Capability means an inbuilt feature, so you can simply use it and you can customize it and use it for your robot. Okay, and another thing is the rows perception, meaning like using the visual sensors like lidar, depth camera. You can implement features like this, like you can create the 3D map of the environment. Okay, so these are the videos taken, data taken from an autonomous robot, self-driving car robot. You can see the 3D map of the environment. Okay, so these all things belongs to the rows perception. Okay, so we have seen three capabilities: rows navigation, manipulation, and perception. Okay, then the final thing in the equation was ecosystem. It's meaning like a lot of developers are using it. Then there are a lot of site, like there is a site called wiki.rows.org, which is basically having the tutorials. Then we have the answers.rows.org, which is having the we will get support like Stack Overflow. Okay, then these are the operating system that is supporting ROS, Ubuntu, Debian. Then these OS will also support, but that is in experimental phase. Okay, now we have covered most of the aspect of rows. Now we can just quickly go through some of the historical aspect of rows and who created it, what are the different distribution, those kind of stuff. So we can quickly go through it. So mainly the project actually started in Stanford. Okay, the original author is called Morgan Quigley. Okay, so this is a person who started the ROS project, but initially the name was not ROS, but a major development was happened in a company called Willow Garage. Okay, so major development was happened in 2008 to 2013. So they started the ROS project. Okay, it's called the Willow Garage, and they have created this robot, these Willow Garage people. Currently, it is maintained by an foundation called Open Robotics. Okay, ROS is maintaining and developing by Open Robotics. Okay, yes, and this is a team. Morgan Quigley is there. Brian Jerky, he's a CEO. Okay, yeah, I'm just skipping this also, and these are the distribution. Okay, so there are different versions of ROS, meaning distribution, meaning it is having a version set of ROS program. It's similar to like if you say Windows 7, Windows 10, Windows 8. So these are different versions of Windows, right? And we have Ubuntu 20.04, 16.04. So we can say these are different versions of Ubuntu, right? But if you check Ubuntu, Debian, then those are called the distribution. These are the different distributions of Linux. Okay, so similar to that, we have the ROS distribution. It is having a set of versioned ROS programs. Okay, and these are some of the ROS distribution, guys, from 2010. You can see this letter is changing. 2010 ROS Sea Turtle. I think I have started from Sea Turtle or Diamond Black. 2011 it's Electric, then Furade, then Groovy, Hydro, Indigo, Jade, Kinetic, Luna, Melodic, then Noitic. Okay, currently it's Noitic. Okay, and there is another set of ROS distributions called ROS 2. Okay, so the ROS Noitic is ROS 1 and ROS 2 is there. Okay, that is actually started in 2018 or so, and this is like a refined version of ROS 1. Okay, which is fixing some of the issues that is facing on ROS 1, and this is still on development, but the latest version of ROS 2 is Foxy. Okay, yes, and I'm showing some robots that is supporting ROS. I'm just quickly go through it. These are some of the robots that is completely working on ROS. Okay, it's called the PR2, then it's called the Turtle Board, Okay, and these are some of the other robots supporting ROS. Okay, and this is Robonaut. This is from NASA. They have implemented the first software prototype in ROS. And these are some of the robotic arms supporting ROS. So there are many robots. I just picked few. Then Husky Robot, Piney 3DX. These are some famous robot platforms that is supporting those. And these are some robot demos, guys. I'm just skipping it, and I will show you these demos during Q&A. Okay, and these are some sensors supporting ROS. Okay. And these are some of the I/O boards supporting ROS. We can interface Arduino board to ROS. We have the Tivasi Launchpad, Fitjet board. These all boards can easily interface to ROS. Okay. And the important slide. So who all are using ROS? Okay. So in my knowledge, most of the big companies are using ROS. I personally know in India, there is a TCS group that is doing ROS-based research, then Wipro, then most of the IT companies are having a wing who are doing ROS-based development, but it's small actually, but they are all doing it, okay? And if you take the companies abroad, there are a lot of companies working in ROS. Okay, so if you take US or UK, there are a lot of robotics companies, and most of the companies are using ROS. Okay, so Intel, you know, Intel, then Qualcomm, then Bosch, all these companies are using ROS. I mean, they may not be, I mean, using, I mean, for all purpose, but for robotic applications, they are using ROS. Okay. So mainly ROS is currently using by researchers, students, professional, hobbyists, and the sensor vendors. Okay, so if some companies are providing a sensor or actuators, they will provide the ROS interface for that. Okay, so these guys are using ROS, and I just put some job opportunities, like it's from actually from US. So there are a lot of companies that provide opportunities for ROS developers. So this is an opportunity from Hyperloop in US. It's a random job opportunity. I just mentioned like they are looking for ROS developers. Okay. And regarding the future scope of ROS and robot programming is that, like when Microsoft started the Windows operating system, you know, at that time, Bill Gates actually said the possibility of a software. Okay, so now Microsoft is one of the biggest company in the world, right? So similar to that, what I'm seeing is that software is having a lot of impact. Okay, so if it is a computer software, or even if it is a robotic software, and if you take the Android application or iOS application, these applications are software, right? So it is having a lot of impact. For example, the Facebook is an application, right? It's a piece of software. Okay, then WhatsApp. So these all are software. So what I'm seeing is I'm seeing great impact for the robotic software also. Okay, so ROS is one of the framework that we can use to implement these robot applications. Okay, I'm not saying ROS is everything. So ROS is one tool which we can use for implementing robot application. Okay, so it's one of the popular tool. Okay, so there are a lot of opportunities coming for ROS developers in India as well as US. I will say US, a lot of opportunities. In India, we can see opportunities for ROS for startups mainly. Okay, and now there is ROSCon, guys, like it's called ROS conference. Okay, so in each year there is ROS conference happening, and this is ROSCon 2019. So I just released my new book called ROS Robotics Project Second Edition, and he's a CEO of Open Robotics. So I just put the pic, and I just put the link because in ROSCon, if you just go to this website, you can see a lot of talks from different ROS developers. Okay, you can see a lot of new ideas. Okay, so that's all the basic things. Now I am planning to show you the demos. Okay, so in between, you can start asking question. Okay, I will show the demo in between. If you have any question, you can just put it in chat box, or you can just ask. Okay, so you can just ask question, guys. During this time, I can show you some interesting demos. Yes, time for question. So I will show you some demos in between. So please let me know if you have any question, guys. So let me start some simulation. So the first demo that I'm going to show you is that how to simulate a robot in ROS. Okay, so there are few questions like which ROS distribution to install for beginner. So for a start, I think I will prefer ROS Noitic. Okay, ROS Noitic will be good for a start. Okay, yeah. So is there any network issue, guys? Am I audible properly?
Yes, sir.
Okay, okay. Okay, so this is one simulation using, I mentioned about Gazebo, right? Gazebo simulator. So this is a Gazebo simulator, and using this, you can able to simulate a robot. So here the robot is called Turtlebot 3. Okay, this is a famous educational robot. Okay, so I can show you how to navigate, how to make the robot autonomous. Let's see. Okay. Let me see whether it is working or not. Okay, perfect. So here you can see the RVs. Okay, so this is the RVs that I have introduced. So RVs is called ROS Visualizer. I mentioned that this is a tool in ROS in order to visualize the data of robot. So here you can see, you can visualize a robot, then the map, all the aspect of the navigation, you can visualize inside the RVs. Okay. Yeah. So there is another question. Any basic version of ROS for Windows? Yes, there is a version of ROS for Windows, but the thing is that they are still developing it. Maybe I can show you that. If you just search for ROS Windows, you will get the tutorial for setting up. But it's actually a pain. I will say it will take some time. It's not very easy, but you can able to work with ROS on Windows. I'm not seeing full support for ROS in Windows, but you can able to build ROS in Windows. Yes. So now what I'm trying to show you is that the autonomous navigation capability. Okay, meaning moving the robot from A to B. Okay, just a second. So let me check. So you guys can ask question in between, no issues. So this class is just, I'm just giving some introduction to ROS because this is a very, very big topic. So yeah. Okay. So now you may get an understanding how, knowing Linux and Linux command is useful while working with ROS, because almost we are dealing with the command line interface. Okay. So that's what knowing of Linux commands and those kind of thing is useful to work with ROS. So now you can see there's a map here. Okay, this is a map of this environment. Okay, so what I'm doing is I'm giving a navigation goal. Okay, so let's see what is happening. So now you can see that the robot is path planning to that goal. Okay, and it's reached the goal position. Okay, and around the robot you can find some particles, right? There are some particles. So that is called AMCL particles, that is adaptive Monte Carlo localization. So that is for the localization of the robot. Localization means finding the current robot position with respect to the map. Okay, if I'm giving a goal position here, then the ROS navigation stack does is that it will create a path plan and it will move to that goal position. Okay, you can see the robot is moving. Okay, it is taking care of the obstacles and all. Okay, you can see it is moving in the real world. I mean, this is a simulated world, but if it is a real world also, it will move. Okay, so if you have the real robot, then you can move the robot similar to this this thing that you are seeing in RVs. Okay, so this is one demo, that is the ROS navigation. Okay, now I would like to show you the manipulation, that is like doing inverse kinematics, motion planning, those kind of stuff in a robotic arm. Okay, so let me close this, and I have set up those kind of things in another virtual machine. So let me just take that. It will take some time. So if any question, let me know, guys. Maybe you can unmute your microphone and ask. Okay. So the advantage of using virtual machine is that you can just work inside Windows. Okay, and you can install multiple virtual machines. Like for example, let me show you. So this is my VMware, and inside that I have installed Ubuntu 20.04, 16.04. Okay, so you can install multiple operating system and you can start it. Maybe you can start 2 instances of operating system. It's all according to your computer configuration. If you have good amount of RAM, then PC, processor speed, then you can run even 2 instances of operating system. Okay. Okay, so now I'm going to show you a manipulation example. There is a robot called UR5. So I'm using the simulation of UR5 in order to show you. I don't have the real robot. So let's start the simulation. So don't confuse with the simulation and all. Like you can work with the real robot as well as you can create simulation. Currently, I don't have the real robots with me. So that's why I'm showing the simulation. You can implement the same software in the actual robot. Okay. Okay. Okay, so here is our RVs, the ROS visualizer. Okay, so the objective of this demo is doing path planning. So we have the robot here, and this is a visualization. This is a simulated robot. So let's see, let's path plan the robot from here to here. So if I do the plan, you can see the possible plans. Okay, so this is a plan, and if I do the execute, plan and execute, you can find the robot is moving. Okay, let me show you the simulated robot as well as the planning. So this interface is just for the planning purpose, okay, just for the visualization purpose. And this is the actual robot, okay. So now I don't have the real robot, but if you have the real robot, it will work like similarly. So I'm giving a goal position here, then planning execute. You can see the robot is moving like that. Okay, so these kind of capabilities can easily implement using ROS. Okay. Okay, so let me show you some more moves. Okay. And you can see, like, if you don't want to work with the real robot, okay, and if you want to do the simulation, the advantage is that you can test the working of the robot without hurting the actual hardware. Because if I execute this plan, okay, what is happening is that it is going down, right? You can see the plan, it is going down. So if this plan is executing in the real hardware, then let's see what happened. Okay, so I'm executing the plan. See, the robot actually collided. Okay, so robot actually collided with the surface, and it's failed the plan. The plan is actually failed. Okay, so that is actually happened. So in order to test the real hardware, maybe you can start with the simulation, then you can test this motion plan after the simulation. Okay, guys, so that is a manipulation. Maybe I can show you one more demo that is again related to the autonomous navigation. Okay, so after that we can conclude this session. Okay, so I'm going to show you a warehouse robot. Okay, warehouse robot simulation. Let me take it. Okay, it will take some time to close all these things. Okay, so there is another question. Sir, is there any links to solve the error caused by updating Linux? So I will say updating, upgrading Linux is a painful process. Sometimes it will crash your existing, existing version. So, and there is another problem, like when you try to install packages in Ubuntu, then there may be crashes. Okay, so there may be they may be saying you have to execute this command in order to remove this error. Okay, otherwise you have to check in the Stack Overflow. Commonly, I will be referring like Stack Overflow forums or something in order to solve the issues. Okay. Okay, now let's see a warehouse robot. So this is our warehouse robot, guys, and this is the environment. Okay. Okay. Now I am just starting the localization. Just a second. So this is again autonomous navigation. Okay, it's going from A to B. Let me execute the commands. Okay. So another question, is there any issue with Python 2 and ROS Neutic? Okay, that's a good question. Like in ROS Neutic, the default version of Python is Python 3.x or 3.7. Okay, so the Python version 2.7 is actually like reached the end of life, because it is not, we are not getting the updates anymore for the Python 2.7. Okay, so if you are using Rose Melodic, it's still in Python 2.7. Okay, but the Python is not actively maintaining, the 2.7 is not actively maintaining, or 2.x Python 2 version is not actively maintaining. So it will be good if you can jump to the Python 3 version. Okay, so so there will be issues while working with Python 2 and Rose Nautic, but I think we can make it compatible. But the default version of Python is Python 3. Okay, so our demo is here. So now what I'm doing is, this is our robot. Okay, and I'm giving a goal position here. Let's see what happened. So it has to go through this narrow way. Let's see whether it just goes or not. So I have given a path, and you can see its path planned. Sometimes it will go and sometimes it's not. Let's see what happened in the simulation. Okay. Yeah, nice. It's actually going through that. So this whole process is happening autonomously. I am not doing anything. Okay, it's just going through that path. You can able to see it's going autonomously without any manual control. Okay, so there is no walls here, but in Rose navigation, we can even create the virtual wall. Okay, so the robot will think there is a wall. Okay, so it's reached the call position. So for the pick and place operation, or like transportation of packages from one place to another, we can use the Rose navigation. Okay, maybe I'm giving a big goal position here. Let's see whether it is working or not. It will take some time to path plan. Let's see. Yes, so this is the final plan. Okay. And it's avoiding all the virtual walls here. And you can see the white, just a second, can make it red. You can see this red color, that is basically the laser scan. Okay, so that laser scan is helping the robot to navigate, also to localize. Okay, and it's also taken care of the dynamic obstacle, guys. So if I put an obstacle here, let's see, it will detect that obstacle. See, it is detecting that obstacle. Okay, and it's avoiding it. If I put an obstacle on here, let's see what happens. Sometimes it will fail to. We have to fine tune the parameters. Yeah, now I think it's failed, because we have to fine tune the parameters a little bit, otherwise it will fail. Yeah. Okay, so this is it. So if you have any questions, let me know in the chat box. And yeah, so this is my contact, guys. So if you have any confusion, you can just send me a mail to cuboticslabs@gmail.com. Okay. So, and I'm offering a course in ROSE now. It's like an 8-month course. So you know the vastness of this topic. Okay. So there are a lot of things to discuss actually. So yeah. So if there is any questions or something in future, maybe you can ask. You can send me a mail. Okay. Okay then. So yes.
Thank you, sir. Thank you very much for a very wonderful session.
Okay. Thanks.
So
Thanks for
there,
calling me. Yeah.
so I think there are no more questions. So we'll wind up the session now.
Sure. Sure.
Okay. So the next session is scheduled at 1:30 p.m. Thank you everyone for joining us. Thank you.
Yeah. Thanks everyone. Bye. Yeah.
Good afternoon, Georgina ma'am.
Good afternoon. Can you hear me?
Yeah, miss. Yes, miss.
Shall I try sharing my presentation also?
Yes, ma'am.
Is it visible?
No, miss.
It's not.
No, ma'am, it's not visible now.
Let me just see. Now?
Yes, ma'am.
Okay.
Ma'am, we'll start shortly.
Okay.
Welcome back. Now we are entering the third technical session of today, which is based on Fundamentals of Robotic Vision by Dr. Georgina Binoy Joseph. Dr. Georgina Binoy Joseph is Dean Academics in Charge and Associate Professor in the Department of Electronics of toch Institute of Science and Technology. Her PhD research was in the area of high performance computing hardware. She also holds an MBA degree with specialization in operations management. She has 24 years of experience in industry and teaching. Her experience as production engineer in charge of biomedical products has led to an interest in industrial robotics and automation. Her current research interests include hardware acceleration algorithms and systems for edge computing in fields of computer vision, and has received funding from DST, AICTE, KTU CERT, and IEDC. She is a coordinator of SPAN of the Department of Electronics Test and has conducted more than 40 workshops for students in diverse technical areas including OpenCV, virtual instrumentation, IC design using cadence tools, robotics, and is a trained faculty under the E-Yantra program of MHRD. Now, I hand over the session to Dr. Georgina Binoy Joseph.
Good afternoon, everybody. I hope you can hear me.
Yes,
Am I
miss.
all right.
Yes.
So those of you all who have attended yesterday's session will be familiar with the way I handle the sessions. Mostly my sessions are lab oriented. If we had a laboratory session in an actual STP, not a virtual STP, where you all are in our college and we are conducting the STP, you all would have got an opportunity to try out some of these programs that we were talking yesterday and today. But no harm done, because like I said, yes, in yesterday's workshop, a lot of the software today, they are open source. You had an excellent session in the morning by Mr. Lenton Joseph, who gave you all the details of the open source ROS software, which we had discussed in yesterday's class. So today what we're going to do is, again, I'm going to introduce to you another two open source software, which you all can use free of charge with excellent tutorials and all. So it will be useful for you, particularly in this time of this COVID and all, when we are having time with us to explore different areas. This will be the right time to explore these very, very simple and very, very easy areas. One more thing I wanted to add is we had a first phase of this STTP in the last month. In the month of November, we had this first phase. So in the first phase, my yesterday's session on robot programming using URDF, modeling using URDF, and visualization using RVIS, it was not there, okay? But this session was there. So if there are any common participants who had attended both the phase 1 and phase 2, this is a repeat of what I did in the last session. And since it was well received and there are some new participants in this STTP, we thought we will repeat that, because it will give a lot of people ideas on how to do open source projects in various areas. So with that, let me go to my presentation. I hope the presentation is visible.
Yes, miss. Yes, ma'am.
Okay. So like I said, this is a repetition of what I did in the first phase. So if there are any people in the first phase who do not want to listen to it again, that's fine, no problem. But if you all want to have a quick overview of what we had discussed earlier, let us go through that once again. Okay. So what my session was is on robotic vision. So why robotic vision, and what is robotic vision? Where does it come in all the different terminologies of vision and image processing that we have talked about before is the first thing that we have to see. So what robotic vision does is it uses a combination of camera hardware and computer algorithms to allow the robot to see the world. Okay. So one of the most important capabilities that human beings have is vision, and the ability to interpret information from that and react accordingly. Now, if that thing was taken away from us, it would be a very, very difficult and a very, very horrible thing to happen to us. So similarly, if you want to create at least a semblance of intelligence among robots, then we have to give them the capability of vision. Okay. So under that comes robotic vision. So where is robotic vision? We are learning so many things nowadays. We're hearing so many terms nowadays like computer vision, machine vision, image processing, machine learning, artificial intelligence, so many things that these are all used interchangeably, and there is nothing wrong in using them interchangeably. But I thought, let me just give an overview of what of each of these terms are and where they are placed. Okay, so this is not a hard and fast rule or a hard and fast thing that I'm saying. It is just an idea of where all these things are placed. So this is from one of the excellent articles that we have on the internet in these areas. There are really good blogs and articles on the internet which you can go and access to read about all these very interesting topics. So initially we were used to what is called signal processing. We pick up signals. Signals can be in any form. In the form maybe a microphone signal. I'm speaking to you, my voice is picked up as in the microphone and transformed to an electrical signal. And those signals could be processed to do different things, removing of the noise or maybe changing of the pitch of my voice. All those things could be do. That was called signal processing. And from signal processing, which is a parent science or a parent field, I would say, then we can move into what is called image processing. Image processing is also signal processing, but we are talking about two-dimensional kind of signals with an X component and a Y component, and also time varying. So it could be time varying. We'll have still images or moving images. So image processing is a subfield of signal processing. So that is where we were initially. Okay. And on top of all this comes optics, because when we talk about acquiring images can be acquired in using different methodologies, different forms of camera, different forms of lighting, different forms of focusing and angles. So many things are there. So the underlying physics behind all this comes under the topic of optics. So if we are going to work in depth in the field of vision, then we need to learn all those things also. Okay. So now comes a new thing that is called computer vision. Now, computer vision has contributions from optics, signal processing, machine learning, and even image processing. Okay, parts and bits and pieces of all the things that we have talked of earlier are coming into computer vision. Okay, and computer vision is the parent of what is called machine vision. Okay, and also robotic vision. Now, machine vision and robotic vision have several elements in common. Okay, and there is also a contribution of machine learning to computer vision and even machine learning directly into robotic vision. So each of these terms are something that we need to be familiar about, but even if you use them interchangeably, there is nothing wrong as long as the person you're speaking to is able to comprehend what you're saying. Okay. Now, I am not going into any of the fundamental theories of any of these things, because that is, you may say maybe a 8 to 12 week course itself we have to do. And there are several excellent courses, including courses in NPTEL SWAYAM. There is a course on vision, computer vision by Professor Jayanta Mukhopadhyay of IIT Kharagpur. It's an excellent course that covers all these terms that I spoke about: optics, signal processing, image processing, computer vision, machine learning, machine vision. He covers them all in a 12-week course. It's a really good course. And similarly, there is a section on how robots use vision by Professor D.K. Pratihar. He from IIT Kharagpur. He has his own NPTEL SWAYAM course on robotics. So when there are such material is already available, I am not going to go into those areas because it's been so well taken and it is accessible to anybody. Now I'm just going to go into the practical aspect and how to implement, how to start learning. The same approach that I used for ROS. Before we get bogged down into the details and the equations and the derivations and get frightened, let us straight away go and do something in robotic vision. So now let us once again in little detail understand that diagram. What is the difference, the basic subtle differences between all these things? So if I take image processing and computer vision, how do we compare these two? Image processing was used to or is used to improve the quality of an image. You can enhance an image, you can smooth it, you can sharpen it, you can do contrast stretching. All those things are used to enhance an image or improve the quality of an image. You can do image restoration. Okay, you can even convert it into another format. Sometimes your intensity level or your color levels may not be suitable for the kind of outputs that you want. So you can convert it into another format, like for example, a histogram. You can also change it further for processing. You can do things like flipping it, rotating it, cropping it, so many things you can do. Okay, so that is an image processing. What is computer vision? Computer vision is more about extracting information from images and trying to understand what is there in these images. An example of an image processing technique would probably be to convert a color image into a grayscale. But if I'm going to use computer vision to detect objects in this grayscale image, then that becomes computer vision. Okay, so that is the comparison between image processing and computer vision. But like I said, people do use it interchangeably, and we should not find fault with them for that. Similarly, machine learning and computer vision. Okay, so what is the relationship? Machine learning is a broader field. It does not restrict itself to vision alone. You can have NLP, natural language processing in it. You can have data analytics in it. So many different techniques can be used to do different tasks and make machines a little more intelligent compared to the ones that were there earlier. But the one part of machine learning which focuses on vision is there, and that comes under what is called computer vision. So machine learning basically looks at data, whatever you give it, whether it is vision or speech or any other kind of business data, it just recognizes the patterns inside the data. Okay, and if it has been trained earlier to recognize certain objects or certain things, let us go to images itself. It is easier to explain using images. Suppose your data are images, and if it has been trained to recognize certain objects from the images earlier on itself, you had trained it to recognize some objects, then if you give it a new image, it will be able to tell you if that object that you want to see, if it is there or it is not there. Okay, so it is actually recognizing patterns. It does not know, like us, we look at an object as a whole. We think our brain is looking, our eyes are looking and the brain is processing an object as a whole. But in actual fact, we're looking at patterns inside that object and then comparing with what we have seen before and saying, okay, this is a dog or this is a cat or this is a bus. Okay, so machine learning does not restrict itself to images alone, but it is one of the parents of computer vision. And sometimes your machine learning and computer vision can be used alongside each other. That is, certain components can be using computer vision techniques alone and certain parts can be using machine learning techniques and you can integrate these two things and bring it together. For example, in an industry, you have various parts coming down a conveyor belt. You can use the computer vision to detect those parts. Okay, and then from that, you can use machine learning to you can use it to decide whether the part is good or bad because you have previous knowledge. You have trained it on previous knowledge as to how a good part should be. So what about the difference between machine vision and robotic vision? There are many it's interlocked. It's not disparate actually, but there are certain subtle differences. Now, if you look at machine vision and computer vision is more about developing algorithms and bettering things and getting more and more accurate extraction of objects or recognition of objects or extraction of features, all those kinds of things. It is more about the techniques. Whereas machine vision actually looks at the applications. It takes the techniques that have been developed in computer vision and goes and applies it to a specific problem and then uses it to get a solution for a particular problem. So it is more about an application of the techniques of computer vision rather than development of the techniques in itself. Okay. So for example, in an industry, if you want to build an automatic inspection system or a robot guidance system, then you can use the techniques of computer vision and develop an application. So that is machine vision. Okay. What is robotic vision? It uses almost all the things that we have talked about, optics, signal processing, etc. Everything it takes from, and it becomes a separate discipline as itself. You compare robotic vision and machine vision, you can use the terms interchangeably, but machine vision does not necessarily need to have robotics connected with it. Machine vision can stand alone even apart from robotics. Okay, so if you say a part is placed in front of a camera, a vision sensor, and it is supposed to look at that part and identify some faults in it, maybe some holes or some dimension differences and all. For that, there need not even be a robot anywhere around the place. Okay, so the camera is looking at a part, and that part we are going to find out if it's a good part or a bad part. There is no robot anywhere there. So that is machine vision, but that is not robotic vision. So when we have robotic vision, some important aspects of robotics also comes into it, like the kinematics. You know what kinematics is? Yesterday we have discussed that. So kinematics, now the frame calibration, how the robot is moving, all those things will start coming in. For example, you can control the movement of a robot using the vision sensor as a feedback. So all those things come under robotic vision. So machine vision does not necessarily need to have a robot associated with it. It is merely taking the computer vision techniques and applying it. Okay, it's applying it. It's taking the algorithms and all that and applying it. It is not developing anything new over there, but taking existing techniques and combining it in a form suitable for a particular application. Now, that machine vision can also be extended to robotic vision, in the sense that there will be some aspect of the robotics also coming into this. So if you want to get a very rough way of understanding how this thing works, suppose you look at signal processing domain, the inputs will be electrical signals, the outputs are also electrical signals. If you're talking about image processing, the inputs are images and the outputs are some form of image, in the form of a histogram or in form of a restored image or enhanced image or even a cropped image. Okay, so that maybe a color image has been changed into a gray image. All right. So if you take computer vision, you give in images and you get out information. Okay, you get information or features you get out as the output. Machine learning, what you do? Machine learning, you take in information of features and give out information based on the input information. Machine vision is again images and information is the output. Robotic vision is images as the input and physical action as the output. That's what I said, robot servoing. Now a robot needs to know how to move. So you have a vision sensor and that vision sensor picks up images, and based on that image, the robot navigates the path that it has to do based on some starting point and ending point and obstacles, all those things. So this is what the preliminary discussion. Now let us go straight into the laboratory part of this. Now we have to look at how I'm going to approach this. Okay, so the approach that I'm going to take is, again, like yesterday's session, I'm going to introduce some open source software. Because earlier we used to be restricted to our laboratories because the software that we require to do such processing was very, very expensive. Now, thanks to the open source software movements, we have got a lot of very, very good capability software that we can use. And many alternatives are there. Like yesterday, I introduced only the certain concepts of ROS, how to start using it. Somebody had asked me, what about VBot? Yes, there is a software called VBot. So it is your choice which one to use. We cannot, show you everything. So I thought I will choose one of the very popular software for showing you. And that is why I chose ROS yesterday. Similarly, I have chosen some software for today's session. That does not mean that these are the only software that are available. There are other softwares, and depending upon your interest or your feeling towards a particular software, you can choose that. But basically, everything works in certain common fundamental principles, which you can learn with any one software. Okay, so we will start with an introduction to some select open source software. Then we will go to the fundamental concepts of robotic vision. Again, like I told you, I'm not going into the science and the theory behind this. I'm just going to demonstrate all these concepts using the software. Okay, so this is going to be the approach of this rest of this session. So today, the first software that I would like to introduce, and many of you all would already be using it. So there might be people who are really good at using these things. So please bear with me. And I am just introducing this on the behalf of the people, the faculty, and maybe there are other people over here who are not familiar with this. So for those of you already used it, please bear with me. So the first software that I'm introducing today is OpenCV. It's an open source computer vision and machine learning library. Okay. As of now, there are about 2,400 optimized algorithms already built into the library. Now, that is the beauty of this. See, like I said yesterday, I am from the electronics and communication engineering background, and there may be people over here or from the electrical engineering, mechanical engineering, computer science engineering. Okay, so it does not matter now because things have changed a lot in the sense that you don't need to know very, very in-depth programming or anything like that to take and start using a software. Okay, the libraries are already available. You just need to know how to initially start using a software, how to access the various algorithms inside that, and how to use those algorithms. You don't even need to know how those algorithms are made or programmed inside in the initial stages. Okay, later on, maybe if you are in a very critical situation where you need to choose, should I use this algorithm or that algorithm, then you may need to read up on what is this algorithm and what is that algorithm. For a beginner, you don't need to get frightened about the programming and the algorithms. If you are not at all familiar with those aspects, you can just take and use the already available algorithms in these libraries. That is the beauty of the way they have developed ROS and OpenCV and all. Okay, what all are there inside this? So you have 2D and 3D feature toolkits, facial recognition, mobile robotics, motion analysis. I've written a whole range of the techniques and algorithms that the libraries that are available for you all to take and use. Okay, we may need only one small part of this. For that, you don't really need to know the entire thing. You just take what you want and use it. And like I said in the earlier session also, the community is amazing. OpenCV has an excellent community. You just have to go there and just look. Okay, like things like GitHub, Stack Overflow also do answer questions on OpenCV, but OpenCV itself has a very vibrant community. You can just go there and you just type your doubt on the Google. You don't even need to go to those communities. Just type your questions, your doubts on Google, and it will direct you to somebody else in this world would have already asked that question. Okay, the answer will be there, the solution will be so clearly written, you will be able to handle it yourself. Okay, so where did this OpenCV come from? It came from Intel actually. So Intel in 1999 started working on this. The person who was behind this was Bradsky, and the first release came out in 2000, that is 20 years ago. Okay, it supports a wide variety of programming languages. Our popular one, C++, Python, Java. You can run it very easily on Windows. As a big plus point for us non-Windows, those are people who are not comfortable with other OSs. Windows, it runs on Windows, okay? And it does run on Linux, Android. You can run it on your mobile phones, okay? On your Apple phones, everything you can run it on. What we are going to use today is what is called OpenCV Python. So OpenCV Python is the Python API of OpenCV. Now, I'm more comfortable with Python because it's a very, very simple programming language when compared to the complexities of C++. Okay, but C++ is very fast, but Python is much slower. So OpenCV Python, it combines the best qualities of C++ as well as Python. What it does is, it's actually a Python wrapper around the original C++ implementation. So you are writing your code in Python, but the code is actually running in C++. So C++ is much faster than Python. So now you've got the ease of writing in Python and the code is running in C++. So it is fast. So that is the advantage of OpenCV Python. All right. So OpenCV Python also uses a library called NumPy. Okay. So NumPy is a library for numerical operations. So mostly it will be like the MATLAB. Those who have used MATLAB will know that you have vectors and arrays in MATLAB. Okay, matrices, you're using matrices in MATLAB. So that similar structure this NumPy also has got. So once we are familiar with arrays and vectors and all from MATLAB, which most of us are now, because at some point of time in our life, we will have come across some kind of MATLAB programming. So similar structures are there in NumPy. Okay, and it also has the support of other libraries like SciPy and Matplotlib. Matplotlib is very, very important because it allows us to plot things, which we'll be using today. Okay, so OpenCV Python is a very, very good tool for fast prototyping of computer vision problems. Now, how do you go and install this? This is one of the most easiest things to do. The instructions are there on opencv.org. Okay, it is there, but I summarized the instructions in this slide. You don't even need to remember this. Just see how easy it is and then go to opencv.org and they'll tell you what to do. The first thing you need to do is install Python. Python should be 3.7 or above. Okay, now we have Python 3.9, which is the latest. So you install Python in whatever way that you want. I have installed Python as a Python shell itself. That's how I did it. Okay. Then in your command prompt, or Windows command prompt, you just install OpenCV Python using the following commands. Okay. So pip install OpenCV Python, and another 3-4 instructions are there. Pip install. Pip is a packet manager for your Python. Okay. And last, you install matplotlib. These instructions are there in the installation page of opencv.org. That's all there is. Right? Installation of Python is extremely simple. They will guide you through the process. And once Python is installed, go to the command prompt of your computer and there just type out pip install opencv-python and your OpenCV gets installed. Okay, it will take some time because many packages are involved in it. So it will take some time. You cannot do it in 2 minutes or 3 minutes. Otherwise, I would have demonstrated it to you. It will take some time. But you can see that this is just a single instruction. There's a packet manager for Python and that will do all the work for you. Now, imutil, scipy, scikit image and all, maybe you will not require in the immediate stages of your using OpenCV Python. Matplotlib you will need, but still, once you install all these things, then later on you need not go back and try to install all these things. So better to install all the above packages. Now, let us start with a few basic programs. Okay, so the image processing is a very vast field. Okay, I cannot cover everything in that. So I thought I would generally show you some basic programs. How does it look? People who are really good with image processing and OpenCV Python, they probably find this very boring. So please excuse me for that. For those who are starting off, I am using the basic programs to introduce you into this OpenCV Python. So it will be very simple for you all to understand. So the first program that we are going to see is how to read an image. Okay. Then how to save an image into your computer. Okay. You're reading an image, how to save an image. Okay. And how to display that image, how to do some kind of processing on that image. Okay, that is what we're going to do and see in the first. So here afterwards, what I'm going to do is I'm going to go out of slideshow. I will not be coming back into slideshow. So I hope the slides will be visible to you because it will be difficult for me to keep jumping between slideshow and the programs. So I'm going out of slideshow right now and I'm going to the Python shell, which I've already opened and kept. So all you need to do is once you've installed Python, in your search in your Windows, just type Python and your Python will open. My Python version is 3.7.4. The shell will open. Okay. So let me run one of the first program file that we want. All right. So what is this program file like? What does it say? So I told you that your OpenCV Python works on images just like MATLAB does in the form of arrays. Okay, and the arrays are from the support for the numerical computations is from a library called NumPy. Okay, so we have to bring that NumPy into our Python. So import NumPy as NP. Okay, so this is the first statement. Import NumPy as NP. I hope you can see the program. You all can see the program. Can you see the program?
Yes, ma'am.
All right, thank you. All right, so import NumPy as NP is you're importing NumPy, that package, into the into your Python. All right. So also import CV2. Now, what is CV2? CV2 is your OpenCV Python. That particular software you're bringing it into your Python as that. The command for that is import CV2. Okay. Now I have got an image that is stored somewhere. You have to write the path for your image. I want to read that image. Okay. So I want to read that image. So I'm going to say image is equal to anything. Some name you can give. That left hand side is your wish. Image is equal to. In MATLAB, you would have simply said I am read and then given the path of the image. Okay. So instead of that, in OpenCV, we have to give cv2.imread. So every command will have a cv2 appended to it. Okay. So cv2.imread. Then I read that image, and that whatever that image is, that will get stored as an array into image, that image, that variable. Then if you want, I can show that image. I can display that image. So cv2.imshow, two arguments are there for that. One is the name that is going to appear when that image comes, okay, comma image. Okay. So that is the first thing we are doing. The second thing is, suppose you want to convert into grayscale. There are several methods to convert into grayscale. One is you can straight away read it in grayscale itself. That is the same image is equal to, you can see, no? You can write it in the same way and put a comma 0 over there. Comma 0. When you put a comma 0, what happens? What is red is not the original color image. My original image was a color image. Okay. It will be red in grayscale and put over here. Right. That one also we can display. Another thing we can do is, if it is a color image, you can invert its color. We'll see what is an invert its color. When I go back to the slide, we will see you can invert its color. Now, these two commands also, when I go back to the slides, we can see that. So just let me run this program. Just go to run and run the module. All right. So this was your original image. Which one? This brown, these gear patterns that you're seeing, that was your original image. This is the grayscale image. The colors have all gone and you have only shades of gray in them. And this is the inverted image. What is that? We'll go and see what is an inverted image. So coming back to the slide, you can see that you saw the same outputs I've brought into the slide. So in OpenCV, unlike in MATLAB, the color image is not loaded in RGB. Okay, it is loaded in BGR. What is the meaning of that? There are three matrices that represents a color image. Okay, there are three arrays that represent a color image. The first, that is each, you know that images are represented in digital form in the form of pixels. Okay, all of us are familiar with the word pixel, because even when you go to purchase a mobile phone, we'll say we want this many pixel camera. Okay, what a pixel is a picture element. Okay, it's a digitized form of a scene. Okay, when you capture with a digital camera, what you're getting is a digitized form of the scene that you are taking an image of. So you will have a variety of numbers arranged in rows and columns, and the values of those numbers are the pixel values. Okay, so suppose it's a grayscale image. Grayscale means what? Only black, white, and shades of gray. Then each pixel will be represented only by one value. Okay, suppose it's a color image. Each pixel will be represented by three values. Now, three values means you have three separate arrays inside your image. Okay, first one is B, that represents the blue values. The second one represents the green values, and the third represents the red values. Yesterday's session we saw in that assigning a color to your robot. No, you had RGB. In this case, you have to remember OpenCV loads it only in BGR format. Okay, so suppose you find a pixel with value 0, 150, 255. It means its value is, blue value is 0, its green value is 150, and its red value is 255. Okay, now this is what is called the color image. This color image has, each pixel has got three values. The next one, if you see the grayscale image, each pixel has got only one value, represents 0 means black, 255 means white. Okay, now why this 255? Because inside a computer, the numbers are represented in binary. Okay, so zeros and ones. So suppose your your pixel is represented using 8 bits. Okay, using 8 bits. Then the maximum value that it can have is 2 raised to 8 minus 1. That is 256 minus 1. So the maximum value of the pixel is 255 and the minimum value of the pixel is 0. Why is it? Because we are representing each pixel value in 8 bits. Okay, so like that, if it is grayscale, you can have 0 as the minimum value, that is representing totally black value, and 255 that represents pure white. So any number between, maybe 100 or 200 or 75, 35, all those things represent some value of gray between black and white. Similarly, if you're having color, now if you look at the first pixel, it is 0. Okay, you look at that, if pixel value is 0. 0 means blue component itself is not there. Okay, blue component itself is not there. You look at the next one, R, 255. 255 means the red is there in full. Okay, and green only partially it is there. So it's a mixture of light green and really dark red. That is what that particular pixel means. There's no blue component there. Okay, so the grayscale image actually represents what? Only one pixel value between 0 and 255, that is black to white. Now, what is this inverted image? Now, if you take this BGR image and then you put it in RGB form using that convert color, this is what you get. So the original one was BGR. You just take it and put it in, you take this as R and then G and B. This is what it looks like. Okay, so that is the meaning of inverting the color. Now I showed you two statements that were there, and I said we will wait for it in the PPT. These two statements have to be there when we use IMShow. Okay, so the first statement is cv2.waitKey. It's a keyboard binding function, and within the brackets you can have a particular value. Okay, a number, an integer you can have. That is the number of milliseconds this function will wait for a specified keyboard event. Okay, so if, for a keyboard event, if you press a key within that particular time, then the program will continue. But if you give a what is that called, argument as 0, it waits indefinitely for the keystroke. Okay, so what happens is, if we don't give this, that image will appear for a very brief fraction of a second and it will disappear. It will not remain there. If you give this wait key, it will wait indefinitely till you press a key. All right, so that is what is called the cv2 wait key. Along with that, we have to use the cv2.destroy all windows command. This destroys all the windows that we have created. Okay, all the things except for the shell, or it will destroy. You can even give which window you want to destroy. You can give the argument within the brackets. So these two statements will come along with IMShow. It has to be there, otherwise you will not be able to see your image displayed. Okay, now we have seen how to take an image which is saved inside a computer. Okay, and then we have seen how to take it and do certain things with it. All right, now let us see how to take a video. All right, now this video can be stored inside your computer. It can be stored inside your computer, or it can be from your webcam or PyCam or whatever. It can be from some camera. So what you have to do is, if it is from a camera, we will go and see the program, you will have to pass a 0 instead of the video file name. So suppose you're going to try and play a video stored inside your computer, you will have to give the path and the name of the file that you want to play. But if you want to actually take an input from the camera and then use it, then you will have to pass a 0. So let me go back to my Python shell and let me open that program. All right, so look at this. Import cv2 and numpy as np. The order is okay. You can write any one first, it doesn't matter. Now this is the new statement. Cap. Okay, cap is equal to cv2.video capture. So this is equally applicable to taking things from a camera, and it is also applicable to opening a already existing file. See, all the files you have to give the proper extension. So if it is a JPEG file for the still image, you have to say .jpg, or you have to give .png or .tiff, whatever is the format of your image, that has to be given. Now this video is a .mp4 extension file. Okay, so the next statement is checking whether there was any error in this entire process. If cap dot is opened, you know what this cap is? Cap is the name that was given. You can change this name. Okay, so captured, that is why we gave cap over there. If cap dot is opened is equal to false. So what can be happening there? If you're taking from your webcam or any other camera, maybe the camera and your computer are not properly interfaced, or maybe your camera is not working. So if cap dot is opened is equal to false, is the situation where it is not working. It can also be that your path to your video that is stored in your computer is not given correctly. It could be that the video that is there in your computer is corrupted. Now, you can just run this program and then wait and wonder why nothing is being shown. Or you can give a statement like saying that if cap dot is opened is equal to false, you print some error message. It is your wish. You can even just say problem, error, whatever it is you want. This is for not waiting over there, not knowing what to do. Okay. So if that it is not correctly opening, the error message will come. Otherwise, what happens is, while the cap is opened, that means what? While everything is okay. Now this is a video. You have to remember that videos are continuous, right? Continuous. The problem here is ours is a digital system. Our laptops, our microcontrollers are digital systems. So we cannot have continuous instant of times. You cannot have data coming in. You have got to digitize it. And how do you digitize it? You capture frames. Okay. So a whole moving picture is captured in the form of frames, one frame after the other. One frame, after a few milliseconds, you capture the next frame. After a few milliseconds, you capture the next frame. This is like, the games that we used to play when we were young. At the corner of our textbooks or notebooks, we will draw some cartoon-like figure. And small variations you will draw on the next page. And then we'll just flip the pages quickly and it will seem as if a cartoon is moving, right? That is exactly what is happening when we are actually taking a movie, or you're actually taking a video with your cameras. The recording is not recording the data of every instant of time. It is only capturing certain frames. And for a second, if you capture about 20 to 25, for a second, if you capture about 40 to 60 frames per second, then our eyes will not be able to make out that these are not continuous images that are coming. They are series of discrete images that are coming. You're actually seeing a series of still images. Quickly you're seeing, but your eyes are not able to make out that. Okay, so that is what is happening over here. Rit comma frame is equal to cap dot read. What happens here is that rit is a logical value. It will be either true or it will be false. What happens is your camera or your video, whatever you're reading, the frame by frame, it gets stored into what is called frame. You can give another variable name here also. So if this process is okay, then your RET value will be true. If it is true, you can display that. Okay, cv2.im show frame. So the first still picture will appear on your screen. Okay, and then if you do it fast enough, then the still pictures will move so fast, it will seem to you as if it is a continuous picture. So to do that, we use that wait key. Remember that wait key function that we saw? So if cv2.waitKey of 25, just forget about the remaining part. Okay, if cv2.waitKey of 25 means, what happens is 25 milliseconds, it will display one still image to you. Whatever is happening in your video, in between, your camera is capturing something and all in between this 25 milliseconds, but you're not seeing all that. You're seeing only one image for 25 milliseconds. Okay, and after 25 milliseconds, the next still image will come in. You will be seeing that for another 25 milliseconds. Then after 25 milliseconds, the next one will come in. So about 40 frames per second, or we can see if you give a 25 millisecond wait key. Okay, so what happens? It will look to us as if we are seeing a continuous video. Now, if you increase this value or decrease this value, different things will happen. We'll see that in the PPT. Okay, this is for, I want to press a key and I want to get out of this, because this is a continuous process. No, CV2 wait key of 0 is not what we're doing. We're doing CV2 wait key of 25. So this will keep repeating. Now I want to get out of this. Let me say that if I press the Q key, I want to get out of this. Okay, so this thing, no, and OXSFF double equal to odd Q, if they allows me, if I press the Q key, then I'll be able to break the thing and come out. Okay, last, after everything is done, we need to release the camera or release the video and then destroy all the windows. Okay, so that is what is happening in this program. I know it is complex for you all in the first case, but when you all go back and when you all try out, some things that I have said now will remain with you, and it will be very helpful for you all when you all do this. So let me run this module. So this is the original image, or sorry, the original video. Okay, and within even the video, the what is that? Even a video you can convert into grayscale. Okay, a video also can be converted into grayscale. So let me show you how that video was converted in grayscale. See this gray. This is another way of converting into grayscale. Earlier we had said comma 0. No, here we can do this statement: cv2 dot color underscore bgr to gray. For inverting an image, earlier we had said bgr to RGB. Now this is for grayscale. So this is another way of doing a grayscale image. Okay, so very simple techniques if you see to actually acquire a image. Now coming back to the wait key function. So we had given 25 inside that. It means that one frame will wait for 25 milliseconds, and then after 25 milliseconds, a new frame will come in. So 1 by 25 milliseconds is about 40 frames per second. That is good enough for us. Okay, but if you put the wait key function very small, let us say 5 milliseconds, then your video will fast forward. It's actually quite a lot of fun. You can take a video and you can play it fast by simply changing the wait key function. You can actually change the number inside and it will become very fast. Suppose you make the wait key function inside, let's say 50 instead of 25. What happens? The video will go into slow motion. Okay, so you can use about 40 to 60 frames per second for normal operations. You can do a lot of things in OpenCV. You can draw inside OpenCV. You can draw circles and rectangles, and you can write and all that. That and all you can learn. OpenCV has excellent tutorials and manuals. Actually, in fact, many of the programs and many of the images that I'm showing you all, in fact, this image of Messi is taken from the OpenCV tutorial itself. Okay, it's really good. Now, we can access particular pixel values. We can access the image properties. What is the size of the image? How many rows and how many columns of pixels are there? You can access one region of the image. Now just see in the first picture on the top, there is just one ball. If you see on the second picture on the top, you can see two balls. What we have done is we have taken one football. We have identified the region of the image of that football. And then we have copy pasted it on this. Things like this and all we can do. Okay, so here is the image at the bottom is actually, we have taken off completely the red component has been taken out of. So you can see there is no red on the second row, the first image, there is no red at all. In the last one, the second row, the last one, if you see, even the green component has been taken off, only the blue. Okay, so let us go and see how these very simple things can be done. All right, so quickly let me go through this. So img is equal to cv2.imread. Okay, same thing. You can write it as image, anything you want, any names over here. And I'm showing the original image. That is what you saw Messi in color. And I'm also going to find out the shape of the image. What is the meaning of the shape? The shape is how many rows, how many columns. That is print img.shape. Whatever name you have given here, no, that name only will come over here. Okay. Now, what is this? Print img.dtype. It tells you what is the data type of the image. I told you that this current thing we are using 8 bits. Okay. So it will come as UINT8, that is unsigned integer. There is no sign, there is no minus. The value ranges from 0 to 255. So it is an unsigned integer represented using 8 bits. So if I do this, execute this, it will come as UINT8. Okay. I can ask to print the pixel values of a pixel. Let us say the 100th row, 100th column pixel. I can store its value. Px is equal to img 100, 100. I can print that value also. Okay. Now this is that ball, football. No, we are identifying where the ball is. Now this we can do by trial and error, or you can evolve some kind of a heuristic to find out where each thing is. You can do it in any way. Okay. So you can find out by trial and error, or you can develop some kind of a program for that. So the ball in our particular image, that football, is in between the 280 row and the 340 row. Okay, row 280 and 340, and column 330 and column 390. That is where your football is. So maybe this is a bigger section. Part of the grass of the football field also will come in. Okay, so we'll not be able to make it out very easily. So where do we want to go and put this? We want to go and put this on the left side. The actual football was on the right side. We want to go and put it on the left side. So look at this. This 280, we are actually, just to show you the difference, you can actually put this as 280, 340 also. Okay, so it will just go to the left side. Here what we have done is we've raised the football slightly to the top. So instead of pasting the new image of the football in the same rows, we've lifted it slightly, some 7 rows above, 273 to 333. This has to be the same, okay? 280 to 340 is how many rows are there? 60 rows. So 273 to 333 is also 60 rows. They have to be the same. It could have been 270 to 330 also. Just for the fun of it, we have just changed some values and retained those values. Now this is significantly different. The column was 330 to 390. The column starts from the left side 0, it goes on. Okay. So left side to the right, it keeps increasing in number. So your ball was on the right side, right? So that is why it was 330 to 390. We want to now paste it on the left side. So we have to put lesser number. Okay. So this is about 60 columns. So 100 to 160. So the image in pixel values in that row, those rows, columns, those pixels will get replaced by the values that we have stored inside the ball. What are the values stored inside the ball? They correspond to the values of the football and the surrounding ground around it. Okay, so that we can show. Now we can even make all the red pixels 0. Now how do we do that? Now our image is in the format BGR. Okay, B is represented by the number 0. B channel is represented by the number 0. What is this channel? I told you a color image is represented in the form of 3 matrices. Okay, 3 arrays. So the B array is given an index 0, the G array is given an index 1, and the R array is given an index 2. Okay, it's not 1, 2, 3. B is index 0, G is index 1, and R is index 2. So IMG double colon, what is the meaning of that? All rows and columns that of the, what is that called, B channel, all rows and columns of the G channel, we are not going to touch at all. Okay. Of the R channel, that is 2 is representing R, all the rows and the columns. This means all rows. The first column means all rows. The second column means all columns. Of the second index channel, what is the second index channel? Red. That we are going to set as 0. So that is in the red array, all the rows, columns, everywhere we are going to set the pixel values as 0. Whatever it was before, we will set it as 0. So what happens? The red goes out of the image altogether. Similarly, we can write like that, IMG : 1. So that means all the green values will go out. Okay. So you will have an image with only blue in it. So let us run this and see how it looks. Yeah. This is your original, and the original image is hidden underneath here. Okay. Your original image. So this is the image in which you took this region of interest, this football, and placed it. You can see it to the left and slightly to the top if you see that. And okay, this is the image in which the colors have been changed. Because the red has been removed. In this one, the last one, the red and the blue have been, and the green have been removed. So this is only a very small indication of what all you can do. I'm just introducing you. So much of documentation, so much of help is available on the internet. You all can easily take it and do. Now look at this. This is the size of the image. What is the size of the image? 342 rows, 548 columns, 3 channels. Why 3 channels? 1 for blue, 1 for green, 1 for red. Okay, that is the meaning of that. Now what is this UINT8? I've already explained. It is actually unsigned integer 8-bit. And what is this 157, 166, 200? We wanted to see what was the pixel value for pixel 100, 100. 100th row, 100th column pixel. What is the pixel value? That was 157 blue value, 166 green value, and 200 was its red value. Okay. So let us go to some more serious stuff. Now we have sort of gone into the basics. Now when you go into robotic vision, Normally, if you're looking at industrial manipulators or industrial machine vision, if you call it, you don't need much fancy stuff. Okay, you don't really need to take one football from here and put it somewhere else. And those kinds of fancy stuff are just when we learn to make our learning a little more fun. We do all those kinds of things. But when you go into industrial robotics, there are certain basic operations that are only required. You don't need anything really very grand things. And one of the most important basic operations is what is called thresholding. Okay. Now, what is this thresholding? You have a value. Let us take a grayscale image. What is a grayscale image? There is only one matrix, one array. That means that does not have red or green or blue or anything like that. It has only either fully black represented by 0 or fully white represented by 255. Okay, or values in between them. That is called a grayscale image. Okay, you know how to convert an image into a grayscale image. So what let us do is, let us take one value between the 0 and 255 as what is called a threshold value. Okay, so if we say, let us say we will take or some value, maybe 56 or 75, some reason we have chosen a threshold value. How to choose the threshold value and all is there in the literature. You can go and search for that. Some automatic thresholding functions are also there, which we will see now. Okay, so you choose a particular threshold value. If the pixel value is greater than that threshold value, we may assign one value to it. Okay, that pixel, let us say we have chosen 150 as the threshold. If your pixel value is 170, let us say we'll say that one we are going to change its value from 170 and make it 255. Okay, that means what? All pixels whose values are greater than this 150 threshold that we chose, we are going to make it white. Okay, and all pixels that are less than or equal to this 150, we will let us assign some other value, let us say 0. That means they'll all become black. So you will really truly have a black and white picture. It's not grayscale anymore. You will have only 2 pixel values. Either a pixel will be white, that is 255 value, or a pixel will be gray, that is 0 value. Okay, that is threshold. You're converting it into a binary image. Only 2 values are there, white or black. Okay, so let us look at what is this function. That function is called CV2 threshold. The first argument in the function is the image name. Where is this image? What that image name we have to give. The second argument is this threshold value. That's what I said. Let us say 150. The third argument is what should be the maximum value if the pixel is greater than this 150. We were saying 255, then max value will be 255. Okay, and the fourth argument will be what there are many kinds of thresholding. So what are those kinds of thresholding? So let us look at the kinds of thresholding. Now, if you see in the previous slide, this is an image of Sudoku. Okay, so again from the OpenCV tutorial, I have taken this image, I have run it and got this. Now, this is with simple thresholding, the kind that I just told you. We were trying to look at this. This is very dull, right? And I am not able to see it very clearly. You can see lighting problems. These are the problems that are going to come in the industry. Illumination is a very big issue in industry, and that is a science by itself. We have to learn properly. Metallic objects will reflect light. The specular reflections and diffusions and all kinds of problems will come. Okay, so these kinds of techniques like thresholding, filtering, the proper illumination, all we need to learn properly before we actually go and implement systems. Now, if you can see, illumination is really a problem here. If you see the bottom left corner of the image has got less light falling on it, and the top left corner seems to have a lot of light falling on it. Okay, so that is why when we took the simple threshold, you got this. The bottom left and the left portion became black, and the top and the right portions all they became white. Okay, so that is not a good kind of thresholding, right? So there are other kinds of threshold. Lots are there. Okay, I'm just giving you a few. Now, adaptive thresholding is one in which it does not take only the whole image. It does not give one threshold value, because you saw, no, the lighting is different in different parts. So pixel values will be different in different parts. What it will do is it will identify sub-regions in this image. Few pixels it will find out in this image. And for each of those groups of pixels, it will find its own threshold. Okay, so it's not a global threshold, it's more like a local threshold. For where the light is more, one different kind of threshold. Where the light is really less, one kind of threshold. Where there's medium light, another kind of threshold that the software itself does. That is what is called adaptive thresholding. There are two main kinds of adaptive thresholding. One is find the mean of the pixels in the area that you're considering. That is your threshold. Gaussian is a weighted sum of the neighborhood values where the weights are Gaussian. Okay, that is another kind of thresholding. And the block size, you can decide what size should be the neighboring pixels. You can decide that. And there is one more parameter in adaptive thresholding, which is called C, which is a constant that is subtracted from mean or the weighted mean. That again is in your hand. These are this block size and C you can change. Okay. So after running the program, the top diagram was, it's a little better than the previous simple thresholding. No, this is your adaptive mean and this is your adaptive Gaussian. So let us just go and see that program. All right, same thing. What I wrote over there, you read the image, okay? And this is the thresholding function, cv2.threshold. This is what the image that you have read, img. What is this? This is a simple threshold value. I want you to set it to 255 if the value is greater than 127. And what kind of thresholding? Binary thresholding, very simple, basic thresholding. The next one is adaptive thresholding. So you have again which image you want to do thresholding on. What is the maximum value? You don't have to give this 127. This is going to be automatically calculated. So what is the maximum value you want to set to if the pixel value is greater than the threshold? What kind of adaptive thresholding? The mean kind of thresholding, okay? And this whole thing is that indicating the mean kind of thresholding. And this is the block size. What is that? I want to find thresholding for square areas with 11 rows, 11 columns. Okay, 11 rows, 11 columns. That is block size. And this is the variable, the parameter that you subtract from the weighted mean. That is, again, these two things are in your hands. Okay, remaining and all is automatically done. The same thing you can do for Gaussian thresholding, and you can see all these things. Yeah, this is what I showed you. Okay, so let us go quickly and complete the rest of it. You can even extract objects of a particular color. So this is another thing that you may need in robotic vision, I'm just giving you all the things that you can put together. Okay. So how to do this, extracting a particular color? See, this is an image that we have with three different colors in it and a background color of blue. What we do is we create a mask. Okay. To create a mask, we need to identify all the pixels of the color of interest to you. For example, for me, if my color of interest was the green, then I have to create a mask for green. Okay. What is mask? Other than the areas which are green, all other things will be black in color. Wherever there are green pixels, there you will get white. Okay. Now here you're seeing in the first column, the second row, you're seeing the mask for red. That to this particular shade of red. Okay. So this particular shade of red, you can bring in over here a mask, and using this mask, you can AND this mask and the original image. You can AND this top image in the first column and the image in the second row of the first column. You AND them together. Okay. When you AND them together, wherever there is black, all those pixels will go off to black, and wherever there is white, the original color will be retained. So that's why you're seeing this red ball. Within the red ball, you can see the black dot, right? Because of the lighting that was there, the illumination when it was there, when this picture was taken, even though this is a completely perfectly red ball, it looks as if there's a white patch there, and that has indicated as a black in the final extracted object. Now, if this was something that we are using machine vision to detect flaws in a part, a machined part, and that to the part is a reflective part, then if you don't get your illumination proper, this is what you're going to face. Look at this. Okay, if your illumination is, lighting is not proper, a perfect without defect object looks as if it has with a black spot inside it, and it has got a defect in it. Okay, so these are the things that are going to be a problem when we do robotic vision. we don't do any fancy kind of stuff for robotic vision. We are actually trying to get things right in the most basic of ways. Okay. Now you can also draw or track objects. You can draw rectangles and squares around objects. That is not for robotic vision as such. You do all kinds of automation. No, you want to identify a person and that person is walking. You want to track that person. These kinds of techniques can be used. So let us look at this program and we'll see how it looks. Okay, so let us look at this program first. So read the image in the first sentence. Okay, now green. Okay, what is this green? Green is np.uint of 0 to 550. You're defining green as green. Now, how do you define it as green? A numpy array, unsigned integer represented in 8 bits, which is green. The center one. First is B. We don't want blue, so 0. Then you want green, so 255. And then you want, what is that thing called? Don't want red, so 0 there. So green is 0, 255, 0. Okay. So then you can go into another color space called HSV. Okay. Now you have already seen 2 color spaces for images. One is your RGB, which is what we are normally familiar with when you go to buy your TVs or your cameras and all that. We talk about RGB, red, green, blue. Okay, now we saw that OpenCV doesn't look at our images in RGB format. It looks at it in BGR format. Now there are other color spaces like CMY, okay, which is the complement of your RGB. And there's a totally different color space called HSV, hue, saturation, value. Okay, you can read upon this. Now, hue, saturation, value model is easier to use when you want to identify colors. Okay. Now, the last time there was a question is, instead of taking this green value as such, okay, green is 0, 255, 0. Why can't we use tuning? Of course, you can use tuning, but this is a very basic class. I don't want to confuse the people by showing how to do tuning. And first of all, if you are not really conversant with OpenCV, you will just simply be complicating matters by going for tuning. So I'm not using tuning over here. I'm actually specifying the green value as 0, blue, 255, full green, and 0 for red. Okay. Now what we're going to do is this green value we are going to convert into HSV. Okay. CV2.convert color green, CV2.color underscore BGR to HSV. Don't get very scared seeing this. This is available in the tutorial book. This is something that I've picked up from the tutorial book. Commands are there. You don't have to remember any syntax. You can always look into the net and get these commands. Okay. So convert from BGR to HSV and you have got the HSV value of green. You can print it out to see what it is if you want to. Okay. Similarly, you can get the HSV value of red, and you can, the ball look like a magenta ball to me. Okay, so magenta is a combination of blue and red. So I just wrote it as 255, 0, 255. In fact, it's not me who wrote it. The tutorial, it is there. Okay, so if you are not sure what the color is, then that is where the tuning comes in importance. But for a basic class, we will not go there. We know there's a green ball, there's a red ball, and a magenta ball. Okay, and we are going to actually make the mask. Look at this. HSV is equal to convert color of the entire image. So here we were taking the green value and converting it into the HSV value, the red into HSV and the magenta into HSV. But now we are going to take the entire image and convert it from the BGR format to the HSV format. Okay, then we are going to make the mask. For that, we will define a lower green value and an upper green value. So what was the result? Let us go and see. If you look at the presentation, the result of the HSV conversion of green, okay, the result of the HSV conversion of green, I would have got as 60, 255, 255. 60 represents hue, 255 represents saturation, and 255 represents the value. Okay. Now, 60, 255, 255, if you want to make a mask, this is how you go and do it. Okay. You define a lower threshold. So 50, 60 is there, no? Go 10 below it. So 50. The other two, which was 255, 255, you keep it as 50, 50 itself. Okay. Okay. That 50 has nothing to do with this 50. Okay. Just keep it as 50, 50. And the upper green value, instead of 50, it was 60 actually, no? So go 10 above it. So we went 10 below it and made it 50, 10 above it and make it 70, and keep the value, full value here, 255, 255. And then you have to make your mask. Mask underscore green. If you use this command, you will get your mask. After making that mask, what you do, you and that mask and the original image, not the HSV image, and the mask and your original image. What is this anding? I had explained to you. Similarly, you can and for red, you can and for magenta, etc. Okay. For example, now I want to draw a red circle around the green object. Okay. So what I can do is I can use a function called cv2.moments. Okay. So many calculations are done for moments like area, perimeter, centroid, lot of things are calculated and stored inside moments. Okay. So moments, cv2.moments takes one image and makes a lot of calculations on it and stores it inside the variable that you've given, that is moments. Out of that, I want only certain things. Okay. I want the area of the circle. Area is equal to moments of M00. Okay. In this moments that you have stored, M00, that one is the area. Okay. Now let us say why I want to look at areas. Suppose there was some small green dot somewhere. I don't want to draw a circle around that small green dot. I will say that only if the area is greater than a certain value, some value depending on your image. Only if the area is greater than a certain some value represented. This is dimensionless. Okay. It's a representation based on pixels. You can convert it into an actual value by doing other conversions, but this is right now dimensionless. If area is greater than some value, okay, x is equal to moments of M10. M10 gives your x value, okay. That is the centroid, that x coordinate is given by moments M10 divided by area. Similarly, the y coordinate is given by the centroid, it's given by moments of M01 divided by area. Now, all you have to do is draw a circle. Where do you want to draw a circle? I wanted to draw the circle around the green object after I detected it. So, this rest green is my green object image. Okay. Now, this is where the center of the circle is. Int x, comma, int y is the center of the circle. This is the radius of the circle. Okay. This is the radius of the circle. That is up to you to choose. Okay. This is the color of the circle. Now, I wanted a red circle. So, blue 0, green 0, red 255. And the last one is an argument that you pass through for, I will show you what that is. And then you say, I am sure. Let me run this thing. So you can see. All right. So you can see over here something funny has happened. No? The magenta has generated, look at this, a whole series of dots here. Again, because of the blue background and the red ball, that combination has seemed to the software as if there was a magenta color there. Now, if you're going to draw circles, if you don't give that area condition, no, if you're going to draw magenta, around all these things, you'll get circles. Okay, so that is why we gave that area condition. So coming back to the PPT. All right, where were we? Last, I have to finish quickly because I have quite a bit left. Now, edge detection, that's the last thing in my image processing thing. Lots is there. It's a very wide field. It's a very amazing field. You can do a lot of things. You can do edge detection using canny edge detectors. You can use Huff transforms. So many things are there, but I'm going to look at the basic edge detectors. Okay. So there are things called Robert, Pruitt, Sobel, Laplacian. All those are edge detectors. So I've just taken as a sample the Sobel edge detector. Okay. Now, if look at this, this is what is called a mask. Okay. So this mask is placed on our image pixel values, and the center of the mask goes and sits in the center of that area. 1 pixel it goes and sits in. So what happens? All the neighboring areas are multiplied by the mask values. Okay, added together, and that then what happens? That center pixel gets replaced with that value. That is basically what happens. It's difficult for me. There is no time for me to explain and show you. you can just go and look at it. It's a process that is called convolution. Okay, the process that's called convolution, and in 2D convolution is very easy to understand. So mask operators, you just look up at anything in the net, you can see. Okay, so if you see over here, there is this is sy. Okay, this is sy and this is sx. This is what is called a Laplacian detector. This detects edges along the y direction, this detects edges along the x direction, and this detects edges along both the directions. Okay, so all these things you all will have to read upon, because there is not much time for me to explain in detail, or maybe we should have some other kind of STP which looks basically at image processing. So let's see how this is. Look at this. You read the image, okay, read the image. You convert it into grayscale. If it's a color image, you convert it into grayscale. Then you smooth the image. Smoothing the images, you try to remove all the noise. What is noise? Inside your image, you might get fine edges and lines coming up because of problems with illumination, problems with the camera, okay? Maybe any other kind of problems in some processing. You can get small fine lines. So your edge detection will even throw up all those lines. Okay, it will bring all those small, tiny, faint lines also into prominence. So we want to remove all those fine lines. So what we do is we smooth the image using CV2.blur. Okay, and then this is the function for the Sobel. Okay, this is the function for Sobel Y, and this is the function for Laplacian. All these things are available on in the tutorials. So let us see. Look at this. This is your Laplacian. You can see X and Y are same. Okay. This is your Sobel Y. It detects edges in the Y direction. Okay. And the Sobel X detects edges in the X direction. Okay. So this is how, these are some of the key things that you will require, or higher versions of this you will require in the case of image processing for robotic vision. All right. So let me come back to my presentation. Now, where can we use this OpenCV inside a robot? Now, what you can do is you can use a camera. All right, you can use a camera, acquire this image and process it inside some kind of your laptop or your computer system sitting inside. You can do it like that. But if you want to really install it inside the robot itself, if you want to, depending on your application, then OpenCV can be installed in Raspberry Pi. Okay, so there are very useful tutorials to how to install this OpenCV on Raspberry Pi. You have got to install it on the OS which is there inside the Raspberry Pi. Right, earlier I think it was Stretch. Now it is, I think, Raspbian Buster is what is required. So you have to take the latest version and install. So install OpenCV 4. The second one would be better. Install OpenCV 4 on Raspberry Pi 4 Raspbian Buster. One thing that you have to remember is that you have got to follow step by step every instruction they give. No, not without even skipping one instruction, because one small mistake, then you will not be able to figure out why it did not get not running in Raspberry Pi. A lot of students have that problem. Okay, so they will be in a hurry to finish the installation. They will not read the instructions properly, and then simply they will do next, and then it will get a problem. Okay, so that we have to see. So in Raspberry Pi, you can connect your own display and you can actually test your OpenCV programs on them. You can develop the OpenCV on another system and then download it onto the Raspberry Pi, and then you can use another display to test it if you want. Then you can just straight run it. It works. Okay. So next, another thing that I wanted to introduce to you all was computer vision. So before that, I would like to find out if anyone has any doubts. Anyone has any doubts in this area? In this area, anyone has any doubts? Or shall I proceed? Because I'm going to totally different thing. Shall I proceed? All right, so let me just go to the next thing that I wanted to see, that is computer vision goals. Okay, so computer vision is what we're going to see now using machine learning. All right, so in that, we are actually looking at more than we are looking at in OpenCV. Okay? We want to extract information. In OpenCV, we are actually making an image in a suitable form to identify some things from it. Okay? That's still the output is an image. So in computer vision, you take the images as an input, you process it, analyze it, and try to understand and get information from that. So it is a subfield of AI, and it automates the tasks that human visual systems perform. So some of the basic computer vision tasks are image classification and object detection. There are lots and lots more. I thought because of the time restriction, I will just concentrate on image classification, object detection. Okay, so image classification is the computer vision model. Okay, the CNN, convolutional neural network that you're using, will look at the image and tell you what is the main object in that image, provided it has been trained to recognize similar objects. Okay, so suppose in your image, it is an image of a bicycle. If that model, your CNN, has been trained to recognize bicycles, it will tell you it is a bicycle. If it has not been trained on that object, it probably give you some other answer. Okay, that is image classification. Now, what happens if there are more than one main objects in that image? Okay, in that case, better than image classification would be object detection. What happens in object detection? You have objects, you put boxes around those objects, and then it will tell you what is there inside the object. So suppose there's a cycle and there's a bus and then there's a car. If your CNN has been trained to classify, to identify these or recognize these objects, it'll put a box around the bicycle and tell you bicycle, or the car, it'll give you car. It'll also give you the probabilities, how correct it feels it may be. Okay, it will give you the probabilities, the prediction probabilities. So how do we as people handle this particular thing? So many ways are there. You can use Google and TensorFlow Keras. Okay, you can go and use PyTorch. You can use Google Colab as your underlying thing. But I am showing another version, because many of you all might have already attended umpteen number of machine learning workshops, because it is right now the fashion, to learn machine learning. So I thought I will do something a little different, and I'm going to use another platform. Okay, so here what we are going to do is we are going to use Anaconda. So what Anaconda is, it is a package manager. It helps you to easily install different things. Okay, so it installs Python and along with it Jupyter Notebook. Okay, Jupyter Notebook is what we are going to use for typing in our code for the machine learning. So the installation is, you install Anaconda's latest version. Right now it is Python 3.8. Install Anaconda's latest version. When you install this version of Anaconda, just follow the instructions that are given. This is the install page. Just type Anaconda in the Google search, you will get. And then you say installation of Anaconda, you will get it. So install the latest version of Anaconda. Okay, following the instructions properly. It's just very quick. It is very quick. It doesn't take much time at all. Okay, and then once Anaconda is installed, Jupyter Notebook is installed. Okay, so just like you have your command prompt in Windows, there is an Anaconda prompt. So when in Windows you search for Anaconda, you will get like your Ubuntu that I showed yesterday, like the command prompt in Windows, you will get one black terminal. Okay, in that Anaconda prompt, just type Jupyter space notebook. Okay, when you type Jupyter space notebook, a Jupyter notebook will open up. We'll see what that is. Okay, before going there, what are we going to use for machine learning? I told you OpenCV also has machine learning. Okay, OpenCV also has machine learning. Now that you all know what is OpenCV, how to use OpenCV, how to install OpenCV, you can go and look at the machine learning models in OpenCV. So I thought I will show you another what is that called, computer vision library also, which is called Gluon-CV. Okay, Gluon-CV is another computer vision library like OpenCV. It is again open source. So the more you learn, the better it is. No, you can use if you don't want to use OpenCV, you can use Gluon-CV. Okay, so Gluon-CV actually provides us with models for different tasks. It is related to convolutional neural networks mainly. It gives us models for each, separate models for each task: image classification, object detection, semantic segmentation, instant segmentation, etc. It gives us different convolutional neural networks. Okay, so this has got what is called the model zoo. So let us see what it is. If you see over here, this is the website. You just have to type Gluon CV model zoo and you will come here. Okay, so this is Gluon CV's model zoo. So you can see over here that this model zoo has different models for what is that classification, object detection, etc. So let us go and look into classification. All right, when you go to classification, you will see a graph that is given to you. If you see, the x-axis indicates the speed of the model, the y-axis indicates the accuracy. So the higher up you are, the more accurate you are. The more to the right you are, the slower you are. Okay, so I'm sorry, the faster you are, All right, and look at these. These bubbles indicate different convolution neural network models. So you can see dark blue indicates AlexNet. Okay, another shade of blue is darknet. If you see over here, you are seeing ResNet. Various versions of ResNet you're seeing in some kind of colors. So the size of each of these dots that you're seeing indicates the memory usage. The bigger the size, the more the memory that is going to get used. Okay. So from this itself, you can see for your system what is suitable. Okay. So accuracy on the y-axis, speed on the x-axis, and the sides indicates the memory. Color indicates the type of model. So if you just go and place, look at this, you go and place your cursor on that, it will tell you this is model ResNest 200, its throughput is this, its accuracy is this, its device memory requirement is this. Anywhere you go and place, you will get the corresponding information. This is MobileNet V for large. Similarly, you can find models for detection. So if you see, these are the models for detection. Okay, CenterNet, YOLO, SSD, faster RCN, everything is available here, and the beauty of it is it's pre-trained. Okay, so since it's pre-trained, if you just want to start learning machine learning, you can just take it and directly use it. Okay, and once you all have become a little more experts in this, what you can do is you can do a process called transfer learning. Okay, you just modify the last few layers of this particular pre-trained model, and then you can actually see what is the structure of the model, and you can modify the last few layers depending upon your application if you want to get more accuracy. So for starting off, it is enough to use a pre-trained model. So now where are we going to use this? You need a framework. Okay, now like you have TensorFlow, similarly there is another framework which is called Apache MXNet. So it is good to know this because Apache is supported by Amazon Web Services, Intel, Carnegie Mellon, MIT, and many more. Okay, so this Apache MXNet originated as a project by students from very, very big universities in the US. Okay, it was called the Distributed Machine Learning Community. They developed this. And then this MXNet was donated to Apache Open Source Software Foundation. And now Amazon Web Services has completely transferred all its work onto this platform. So it is important for us as faculty to know, and for our students also to know, that this Apache MXNet, how it works. Okay, it is not only for computer vision, it is also for NLP and every other kind of, you have this speech recognition kind of thing, text, all those kinds of things, you can use this Apache MXNet. All right, so again, it supports a lot of different languages like Python, R, C++. All right, and the Gluon CV, that Gluon CV is a library in this ecosystem. So how to install MXNet? Again, very, very simple. You have already installed Anaconda, no? So in that terminal of Anaconda, do pip install mxnet-mkl. This MKL is for Intel CPUs. For other CPUs, AMD or something like that, this hyphen, that will be different. Okay. For Intel CPUs, it is hyphen MKL. Then you just say pip install Gluon CV and then Python. That's about all. If you want to check whether the install, it will be okay because this doesn't take much time. You just type import MXNet, import Gluon CV. If no errors are reported, then your installation is okay. Now, where do you go and find this? It is available in, when you go to this MXNet web pages itself, they will tell you how to do these things. Okay, So let us look at the first problem, image classification. So here we are going to take images from the Gluon CV model zoo. And we are also going to need a training set. Machine learning, what does it do? It takes the convolution neural network and trains it on what? Some data set. Okay, trains it on some data set. So I told you that the models in your Gluon CV model zoo are already pre-trained. The image classification models are pre-trained on what is called ImageNet. Okay, ImageNet is developed by the Princeton University. It has the actual full data set has 22,000 images. Sorry, it's called 22K, 22,000 classes with 14 million images. But most of the models in the Gluon CV models which we are going to use are trained on a smaller data set, 1,000 classes and 1 million images. Okay, and for beginners, it is advisable to use some simple architectures like ResNet or its derivatives and MobileNet. So let us go and see that now. Object classification. So the whole thing is, this is on the cloud. Okay, so this is what your Jupyter notebook looks like. There will be a lot of people among you that who have already used Jupyter notebooks. Okay, so Jupyter notebooks are another way of writing the Python programs you can write. This is Python that is written over here. Okay, what the beauty of this is that the code is organized in various cells. You can see small boxes. For those who are not familiar with this, you can see small boxes. Let me see if I can zoom it. Yep. Right. The code is organized in various boxes, okay, or they're called cells, okay, and you can run each cell. You don't need to run the entire program and then try to debug it on the whole. You can run each cell, debug all its errors, run the next cell, debug its errors, like that you can do. You can also insert cells that are not code, that are text cells that don't need to be run for documentation purposes, okay. So let us quickly go through the code here. Just like we had to import your CV2 for OpenCV, you have to do an import NumPy, okay. We have to import over here certain things. Here we are importing MXNet as MX, okay. We are going to import that Apache MXNet as MX, import Gluon CV as GCV, okay. And we are also have that there's a familiar face here, matplotlib, that is also used in OpenCV. We are going to take it as this is going to plot our images, okay. Now this, if you click on this, if you click on this this I've saved as a HTML page, so I cannot click and run and show you. The reason I did that is some of these steps take a very long time, and you will have to wait till that entire thing runs, because this is on the cloud, So it depends upon the availability of these servers, okay. It's not running on my laptop, it's running on the cloud. So it depends upon the availability and that the bandwidth that we are getting, and also of course it depends upon your local connection also, your Wi-Fi connection also. So what I did was, after running, I have saved it and kept. But if you want to run it, what you have to do is this. You look at the first cell, in one is there, so double click on that. Then it will become a star and it will keep running. Once it runs, a new number will come there. Okay. So first cell you run. The second cell you read the image. There, when you wanted to read, how did you write? cv2.imread. Okay, the same thing only, .imread only, but the thing is, it is mx.image. That's all the difference. That's why I said, if you learn one thing, it becomes very easy to learn the other type also. So mx.image, then .imread, and give the local. So the image that I am giving for this program is the image of one famous volcano called Mount Baker in the US. This is again a standard picture used in many tutorials. So now our model has to recognize this as a volcano. That is the whole point here. Okay. The third cell, you can even combine cells. Okay. You don't have to give certain things in each cell. You can even combine cells. So print type. Okay. Type means what? What is this image? What format is this image in? Okay. This image is in the form of an mxnet.nd array. Your OpenCV images are in the form of NumPy arrays. NumPy arrays are slightly different in the way they are processed in mxnet.nd. mxnet.nd arrays, the way they are arranged, the processing is faster than the NumPy arrays. That is why they use this mxnet.nd arrays. Okay. Next one is print the shape. So the input image that I gave is the same as the previous one. That shape means what? 156 rows, 156 columns, 3 channels. That means what? It is a color image. So now we have to see what this is. Okay, this in when you talk in terms of this Gluon CV and Apache MXNet, we will talk of it as the layout. The layout is HWC. Okay, height, width, and channels. HWC, height means what? Number of rows. Okay, so that is 156. Width means what? Number of columns. So that is 322. And 3 is the number of channels. All right. Now again, print the data type. So again, UINT 8 only, just like your OpenCV, unsigned integer 8 bits. And it is a NumPy type. Even though we are in MXNet, that kind of a format, the data type is a NumPy UINT 8 itself. If you want, you can print the minimum value and the maximum value. Everything is treated as an array in the case of MXNet, and that is why we have got to make it into a scalar. So dot as scalar functions are used to make it into a scalar. Otherwise, we will get over here minimum value is one array, you will get maximum value, you will get another array. Okay, now to visualize the image, there is a slight change. We cannot just say cv2.im show image, and before that you will give the name of the image. Here it is slightly different. Im show only is the keyword that is used, but we are going to plot it using matplotlib. Okay, not cv2. There's no cv2 here, and Gluon CV does not have its plotting tool unlike cv2 has. So we are going to use the matplotlib, that is, we have called it plt, no? So plt.imshow. So the imshow function is coming from matplotlib image. We have to convert it from MXNet ND array to NumPy ND array. That is this function, image.asNumPy, because your matplotlib will not plot MXNet ND arrays. Okay, so this is the image that we have given. This is Mount Baker. Now we are going to go into the actual processing with the neural network. Okay, and that your convolutional neural network has already been trained. Okay, in that ImageNet had what? ImageNet 1K had 1000 classes. In that, one of the classes is the volcano. Okay, it's the volcano. It's already trained. It's a pre-trained image. So this ImageNet, that what is that called? Whatever model you're going to use, requires 4-dimensional images. Now, what is the size of our image? The shape of our image is only 3 dimensions. 156, 322, 3. That is HWC. We need 4D. What is this 4th dimension? To speed up the working of our models, the models have been made to tackle batches of images. Okay, for the training and the testing, validation and all, batches of images are used, not one at a time. Okay, so batches of images means first dimension, second dimension, number of channel and number of images you have to give. For us, we have only 1 image, but still it will not accept because we need to give the number of images. Okay, so we have to convert our 3D image into a 4D image. That is the first thing. Second thing that we have to do is we have to convert the HWC layout, okay, into an NCHW layout. What is N? N is the number of images, which for us is only 1. C is the number of channels. It is 1 if it's a black and white image. It is 3 if it is a color image. H is the number of rows and W is the number of columns. So NCHW we have to do. On the top of that, we also have to normalize our input data. What is normalizing our data? Our data values range from 0 to 255. No, the numbers range from 0 to 255. We want to convert it from 0 to 1. We want to have that only that much because computations will become a little more easier if you have smaller values. So we need to normalize our data. So many things to be done. But all this can be done so easily with a single step. Okay. So all we need to do is this. Image is equal to GCV. GCV is Gluon CV dot data dot transforms dot preset dot ImageNet dot transform underscore eval. What you want to change into the 4D you give inside here. The name of you have stored the thing in image, no? This image is 3-dimensional. I want to convert it into 4D, and on top of that, I want to normalize it. On top of that, I want to change the order from HWC to NCHW. All those things are done in one single step without us knowing using this. Only thing we have to remember is which data set we have been training on, that data set's transforms we have to use. So if you have trained it on ImageNet, you have to use ImageNet. If you have trained it on COCO, you have to use COCO over here. Okay. Now if you print, okay, you can see that this has changed from 3D to 4D. Okay. First is the number N. Only one image, so 1. It's a color image, so 3 channels. So this, look at this. This has changed. What was our original thing? Our original thing was 156,322. Now, why did that become 224? What happens here is that we are actually cropping a big image or extending a smaller image to 224 rows to 224 columns. Why is that done? Because the original ImageNet was trained on such size images, only for that reason, nothing else. And if you see, your data type also has changed. It has changed into a floating point. It is not numpy.uint.8. And in the floating point, your maximum value and minimum values are this. Okay. So much of changes have come to our image just on this one thing. Okay. Now let us take our model. So the model that we are going to do uses ResNet, this version. Okay. Network is equal to, you can do anything here, NW, give any name you want here. Network is equal to gcv.modelzoo get model. Okay. ResNet pre-trained is equal to true. If you give pre-trained is equal to 2 only, you will get a pre-trained model. Otherwise, if you say pre-trained is equal to false, you can get an untrained model. Okay, and you can actually train it on your own data set. Suppose your data set is completely different and you don't want a pre-trained one, you can train it on your own data set. Now, there's another thing that you can do in Gluon CV is you can build your own CNN. You don't have to take any of these existing models. There is provision for you to build your own CNN with a required number of dense layers and fully connected layers and pooling, max pooling, what kind of things you want, you can create your own neural network also. This is only for beginners. Okay. Now, this is the thing that takes a very long time. Okay. That is why I showed it like this. Now, you just have to give prediction is equal to network of image. Okay. So, this is your network. ResNet pre-trained is your network. You give your image to that network and tell it to give its prediction. Just one line, prediction is equal to network of image. So then you print the prediction. Okay. So what you're getting is one array, 1, 1000. It has a shape 1, 1000. That means you have got one image and there are 1000 classes in your ImageNet, right? There are 1000 classes. It was ImageNet 1K. So 1000 classes will come. And for each class, the predicted probability also will come. Okay. It will say most of it will be 0. Only the first few will have some values, but all the 1000 classes will come. Okay. So now what we want to do, our input has just one image. No? So what we will do, we will take the first one. Prediction is equal to prediction of 0. Okay. So only one was there, you will get the prediction of that first one. All right. So now what you can do is, if you want, you can just see what this thing looks like. What is this prediction looking like? I said that the prediction will look like probabilities, right? So let us just print a few of the prediction values. Print prediction 952. You skip 950 values because there are 1000 classes. No, just type the last 50 values. Anything you can give here. Okay, 95020. You can type the first few. You can do anything you want. Look at the funny numbers that you're getting. Something really weird you're getting over here. All right. So these things are very difficult for us to understand. These numbers are called logics. It's not very easy for us to understand this. Now, this is not the probability that we expected, right? So there is a function called the softmax function. All right. It takes these logics and converts them into something that looks like probabilities. So it will transform these values, these logics values, into something that lies between 0 and 1, which can be interpreted as probabilities. So look at this. Probability is equal to mx.nd.softmax of prediction. Now the same values, no, if you print once again, okay, the same values, if you print once again, you can see these are the values, okay. Most of them will be 0. Only a few of them will be non-zero. What is the meaning of all this? The 950th class, okay, whatever was the 950th class, our input image is definitely not that. Probability is 0. The 951st class, our input image is not that also. Now, somewhere in this, there is a 0.04 probability of our image being this particular class. But we don't know what these particular classes are, right? So let us go and see how to find out what these classes are. If you want to find out what each class is, you just have to write network.classes within brackets, whichever class number you want to know what it is. So I just wrote network.classes 567. It so happened that the 567th class in ImageNet 1K is a frying pan. Okay. So you can use this set of statements over here to identify the top classes and print their names and give their probabilities in the form of a percentage. Okay. So for I in the range K, you can give what value of K you want. Okay. And then the K top indices, I have given K as 5. So the K top indices 1, 2, 3, 4, 5 and their names. What class names are there? Okay. Alp, volcano, Alp, lakeside. And what is the probability? The number would have come as 0.58. We are multiplying it by 100 to get it into percentage. So what this ResNet is telling me is the input image that I gave is 58% chance of it being a volcano, 4.29% chance of it being the Alps, 2.35 chance of it being lakeside, and so on. It will give a list of all the 1,000 classes with different percentages. The lower you go, the more the chance the percentages will be 0. So this is what is called object classification. Similarly, you can do what is called object detection. Okay, I'm not going, I think we have almost reaching the time. So what I'm going to do is, I'm just going to show you what it will look like and what are the differences. Okay, I won't go into the details. This is a very standard image that is used for object detection. There is a dog, a bicycle, and a car in the background. Okay, now let us go and see. Now from your model zoo, you will have to choose a detection model. Okay, we can choose some detection model for it. So let us see how it looks. The model that we chose is YOLO 3 combined with DarkNet S53. Okay, YOLO 3 combined with DarkNet 53, and it has been trained on the COCO data set. Okay, so let us go and see what that is. Object detection. The COCO data set stands for Common Objects in Context, and the basic architectures you can use for beginners are SSD, YOLO, Faster, RCNN. You will start hearing your students speaking with all these names. So you just should understand that they are only various forms of neural networks that are suitable for various applications. Okay, so the model that is used here is this YOLO _ DarkNet 53 COCO. Okay, and then what we have to do, we have to transform this. No, we remember the transformation. Look at this. Oh yeah, this is what I said. You have to be careful there. Everything is okay except the fact that if you see over here, you have to change this. There I had put it as ImageNet. Here you have put it as YOLO. Even though the data set is COCO, here YOLO. So for each thing that you use, this command will change. So you have to change the command suitably. But basically what is happening is the same. The HCW layout is being changed to NCHW layout. Okay, so take the network, take the prediction. Okay, now your prediction will not be like a probability value with a class name. There will be 3 things that are coming in it. Okay, your prediction is a tuple. All right, it has got 3 MNet ND arrays. The first array is what object class it is, just like we did for classification. So dog, bicycle, car, it will come. The first array is that. Okay, the second array will contain the probabilities of the classes. Okay, and the last array will give the coordinates of the boxes that we are going to draw around the box. So it's different. There you just had the probabilities. Here you will have 3 arrays. That is, it's a tuple. A first array is the class indices. The next array is the class probabilities, and the next array contains the bounding box operator. So we can see what all these things are. Okay, let us go and see. This is what it looks like. Look at this. Class indices. You can find out what the classes are. So you can, all these are the network dot classes. All the classes that are there in the COCO are being displayed over here. And what is this? This is what the probabilities will look like. And this is what the bounding boxes look like. Now, how this is given? This is given as the opposing two diagonally opposite corners of the rectangle that you're going to draw. The top left vertex and the bottom right vertex, the coordinates are given. The x coordinates of the top left vertex of the rectangle and the y coordinate of the same. The x coordinate of the bottom left vertex and the y coordinate of the same are given. So you can see this is the output that comes here. And the way you plot this is also slightly different. This is the command for plotting this. So you can get this. Okay. So like I said, there are a lot of amazing tutorials and help because everybody wants us to use their products. Why are they wanting us to use their products? Because they want us to be ready, or our students to be ready to work as soon as they go. Okay. So they don't want to spend money training the students. So they are giving courses. You know, AWS has its own set of extremely good courses. I have gone through a lot of AWS courses. They're very, very good. You can audit the courses, or you can pay money and you can attend the courses for the certificate. They teach it, you know, at the smallest and the most, the person who really doesn't know anything also can actually start off on the AWS things. Okay, so this, I think AWS courses are available on Coursera. So from a computer vision task, this is semantic segmentation. Object detection, you know what it is. Semantic segmentation is, if you want to identify the objects, all the pixels inside that objects will be converted into one color. Okay, so look at the dog. All red pixels indicate their dog pixels. All blue pixels indicate their goat pixels or sheep pixels, whatever they are. Okay, but the only thing is, they does not differentiate between instances of the same image. So suppose there are 3 sheep here, all 3 will be blue in color. Whereas instance segmentation, for each instant of the same object also, each instance of the same object, it will give a different color for the pixels. So these are the different, all these have got their own CNNs. Okay. Now robotic vision, again, like I told you earlier also, if you're looking at a driverless car, an autonomous drone, and all those kinds of things, you know, this you may need all the things that we saw here. Okay, but for a basic industrial robotic vision application, other things may be more important, like illumination and field of view and focusing and okay, removal of noise and all those things. So many ways in which you can do things in robotic vision. And we saw Ross yesterday. We saw Lentin sir telling us OpenCV can be used along with ROS. Okay, ROS provides OpenCV. It provides a bridge to integrate OpenCV data into ROS. As similarly, a communication bridge is there. It's called the CV bridge between OpenCV and ROS. Similarly, you have in ROS, you have Point Cloud Library. Other things that you can use are Google Colab. Okay. And Colab notebooks are very similar to Jupyter notebooks. They're actually Jupyter notebooks hosted by the Google Colab. Okay, and TensorFlow is one you can use along with this. And there is a Keras that provides a Python interface for this TensorFlow library. There is PyTorch. There are different options available to us. And the beauty of it is we are here at the right time to learn, because there are excellent courses that are available for us to go ahead and do this, learn it on our own. You don't really need to have the, I'm so sorry, you don't really need to have you don't really need to have the go to any place and learn. You can learn it on your own. Just have the confidence. It will take time initially, and after that you'll say, oh my God, was there only this thing to learn? Okay, so it's not a very difficult thing at all. So go ahead and start learning.
Thank you, ma'am.
Yes.
Georgina, ma'am, thank you.
Yeah, thank you, miss. So I see only one question by Raghavan sir.
Yes.
So Good evening, sir. Thank you for attending the session for the second time. I hope you did not get too bored by it. So the question.
I was longing for it.
Thank you very much, sir. You are very kind and very patient. So you were asking for the best book for Python for self-learning. Sir, actually, I'll be very honest with you, I didn't really use any textbook, because what happened was when I in fact used tutorials on the internet. And there again, age is a factor for many of us. The same thing is, you learn the syntax, unlike students who are sitting in the classroom and learning the syntax and all the commands and writing the exam. For us to keep it in memory is very difficult. So I went through the Python tutorials and I found myself forgetting what I learned before. Then what I thought I will go to some application. And one of the applications I required at that point of time was image processing using OpenCV. And that required Python. So what was required for that, I started learning. And that is a very, very odd way in which I learned Python. So
okay.
Maybe
Can you please send me afterwards the link of that website?
Yes, sir. Yes, sir. That tutorials, I will send you the link of the website.
Okay.
Both I will send. OpenCV I will send, and as well as the Python tutorials. Both I will send by mail. I have your mail ID, no, so I will send it to you.
One more thing. If
Yes,
you are given a choice of choosing MATLAB or Python, which one will you choose?
Like I said, when I did my PhD research, I did my entire work on MATLAB, because at that particular point of time, that was very much earlier, I was not familiar with Python. So I did it on MATLAB. Okay, but now that I'm familiar with Python, I feel both are equally easy. The only problem is I do not have Python or MATLAB on my system. I'll have to sit and work in a laboratory, or I'll have to be using an illegal version of it, which is not right, which we should not encourage our students also to use. Particularly now that we have Python available, if I need to do anything further, I will do it only in Python, because that is anyway open source, so that's no problem. There is another very good software that a lot of people use called R. I am not familiar with that, but very many people are very happy with R. And also there is another image processing software called ImageJ. That is, these two things are used. R mainly for statistics related things, and ImageJ for biological images and all they use. But I personally have not used it, but I've heard of a lot of people being very happy with these two open source. We are living in a very, very good age right now, because lots of open source things are there, and very good people to support us are there. And then ACT giving us things like this, opportunities like this. Only thing is, we should be willing to work a little hard. If you are willing to work hard, I don't think there is anything that is thing. And you are a very good example of that, sir. How patiently you have sat through every session. That shows, that is giving us the, that is the right way to go. It is telling us you're an inspiration for us. Thank you very much.
One more thing, madam. Is
Yes,
there anything that Python can do exclusively computation which MATLAB cannot do?
That I'm not sure. So like I told you, I am not an expert in any of these things. I just use MATLAB as I require it and Python as I require it. So I would not be able to say. Maybe I can search on the net and let you know, sir, if there is any limitations to Python.
Thank you.
I'll do that, sir. I'll do that. If there are no more questions, then thank you very much to the participants, and especially to the organizers who have, been a very big support. Thank you very much. And thank you, Deepa Miss, for all your support.
Thank you very much, ma'am, for a very wonderful session. Thank you very much. So with this, we are winding up today's STTP. The next session is scheduled at 10 a.m. tomorrow. Thank you for joining us. The feedback is available. Feedback as well as the attendance is available in the chat box. Thank you.